And now we're recording, okay? So what you see on the screen and what I say are being recorded in sync, and later you'll see it on Blackboard. So before we actually get started, let me go back and show you on Blackboard, okay? I'll look at the last physical science class that I taught. I'll show you their Blackboard. I don't have yours set up yet, but I'll show you how it looks, if it'll come up. This is how yours will look as soon as I get yours done. I had hoped to do it today, but like I said, everybody and their brother came by when I was trying to get this done. So, okay. Here we go. I want to go to Blackboard. All right. Well, all right. Now, I won't be able to, I regret sometimes doing this because, hey, they hold more on this one. Okay. This is this class. We'll look at last fall's class. This is how yours will look. Yours doesn't look like this yet, but this is what it is. All right, when you go to Blackboard, now this is not your class. This is last fall's class. But when you go to Blackboard, yours will look like this. And go down here to the tab here that says Content. Okay? And click on the content. I think I already marked you here because I knew you were next door. Oh, well, it's not on that sheet. It's on this one. Thank you. Okay. Yeah, I marked you here. Okay. So this is, again, yours doesn't look like this yet, but hopefully it will. Maybe not by Thursday. Hopefully after the weekend it will. Okay? Under Content, you'll see Syllabus. It's not there yet. It's got one more correction to make the syllabus before I can put it out there. Then you have Research Paper Instructions. We'll talk about both of these today. I'll have my locator card. I don't have the last changes made on that, but as soon as I do, I'll put it there. And then you'll have YouTube videos. Okay? If you go to YouTube videos and click on this, then you'll see coming up all these videos. Now, these are the ones from last fall. Okay? But there was Physical Science Chapter 1. That's where we're going. Well, actually, today we're going to start with syllabus. Okay? And then there will be, it'll do like this. Each one of these is a separate class. Now, some of the classes will have labs with them. I'll try to remember to put that. And those labs will be at the end. Okay? And others will just be classes. Okay? So that's how it'll look. All you have to do is click, and it goes there. Okay? And then you pull that up, and you see this is 3 hours and 50 minutes of recording, 3 hours 43. Okay. The old system we used to have was called Integrity, and Integrity, you could pick the slide you wanted to go to and only watch the pieces you wanted to. Now this one, you've looked at some of these. Isn't there a thing you can just sort of guess where it is? And yeah, so you don't have to watch it all, but you just have to sort of guess where it is in the class and hit that on the time bar. You know how to run video, do video. So nothing new for you. So that's what it'll look like, and that's how you'll access it. Okay? It's pretty simple, but you'll need to know your, I hope I just signed, yeah, I signed up. How to access Blackboard. Okay. That's all I'm going to do on Blackboard. All right, let's get back to the syllabus. It's in here somewhere. That's not it. That's not it. Had I called it up yet? No, maybe I haven't. So let me call up the syllabus. Let me just see. There it is, I think. So I don't need, man, I got too many things open. Okay, this is the one I don't need, I think. I might need it later, but I don't need it now. Okay. That's it. Okay. There. I thought I had called it up. Here it is. All right, this is where we had planned to start today. We are about 30 minutes later than what I had hoped to be. This is the syllabus for this course, mostly finished. Not quite. I'll show you where the changes are. I got most of this done, part of this done during my break between classes, but I did not quite get to finish it. I had just too many interruptions. Okay, this is spring 2017, second midterm. Physical Science 112, Physical Science 2. It's a 4-credit hour course. 3 of these they call theory credit hours. 1 is a lab credit hour, but you have 5 contact hours a day. Okay, it shouldn't be a day. It's really 4.5 because these 3 credit hours, they do 2 hours and, an hour and 15 minutes rather than an hour and a half. So you have time between classes. So that would be, 2 of those. Hour and 15, that adds up to 2:30. So that's why rather than 5 credit hour contact hours, it's 4.5 contact hours. Okay? The lab is 2 hours every day, but we won't always be in lab, but that's where you only get 1 credit hour. You get 3 credit hours for the 2.5 hours of theory. You get 1 credit hour for the 2 hours of lab. It sounds a little backwards, but it's okay. The class meeting times, I did get corrected. 1:15 to 3:45 is technically the class, and 3:45 to 5:45 is technically the lab. In fact, what we're doing now is more like lab stuff than it is class stuff because we're not doing any physical science. But today's an exceptional day. Okay, my name is Charles Fowler, okay? And here's my contact policy, or that's what they call it anyway. And Brittany has heard this many times before, and she probably will laugh at me and say amen when I say some of this. All right. My phone number here on the Bessemer campus is 929-3449. Okay? I'm here Monday through Thursday. Okay? You'll see my office hours later. Okay? On Fridays, most Fridays, I'm on the Birmingham campus. My number there is 929-6409. Okay? Now, I used to say, if I don't answer my phone, leave a voicemail message. I've quit doing that because right now I'm so stinking far behind on voicemails. If you leave a voicemail, who knows what year it'll be before I'll get to hear it, So don't even bother, okay? What I'll tell you right now in just a couple of minutes, my office hours, I'll say this. If you're going to call during my office hours. If I'm not in my office, I'm not going to hear the phone, and who knows when I'll hear the voicemail. Now, if I'm during office hours I'm not in, hang up and call back during office hours. Maybe give me 5-10 minutes. I may have gone down to make copies. Anything could have happened, but I should be back in my office most of the time during office hours. Okay, so don't bother leaving voice messages. Who knows when I'll hear it. Don't leave any voice message for me on Friday at that number because that's not my number anymore. I use an office over there that belongs to someone else, and it goes to her voicemail, not to mine. So I will never hear that. I can't access her voicemail. Okay, so don't leave it on Friday, but if you need to talk with me on Friday, try the number. If I'm not there, hang up and try back in 5 or 10 minutes. If I'm not going to be there, I'm going to let you know on Thursday. Okay. Now, my email. That's my email, and it's good. The trouble is I'm really far behind on emails too now, but leave me emails. I will see them eventually, a lot sooner than I'll hear voicemails, okay? So emails are fine, but right now I'm really far behind. My office on this campus is in room 265, okay? To get to 265, you go out of this, here's this classroom right here on the corner. You go out the door here, take a left, go down this half flight of stairs here. By the way, that's the corridor that goes across the financial services and that part. Go past that, the last office on the left is 265. Just before you get to the stairwell, just past the mechanical room, just past classroom 263, right across from the orientation classroom 256. That's my office right there. Okay? And that's how you get there. So, that's on the Bessemer campus. Monday through Thursday, as you'll see the office hours down here. On Fridays, I'm in the academic building, which is also called the B building on the Birmingham campus. Now, are y'all familiar with Birmingham campus? Not at all? A little bit. Okay. There's two campuses in Birmingham. There's what they call the West campus and the East campus. East campus is right across from Manoa Stadium and stuff like that. The West campus is really the kind of the main campus. It's not the oldest campus, but it's the one that came later. It's where the president's office is. All the honchos live there, except for nursing and some of the others. They're real close to each other, just across Wilson Road and down a little bit. So I'm on the West campus. And the main part of the campus, I would say, are that 4 buildings that make a quad in the middle of a circle. You drive one way around, and in the middle are 4 buildings that make a quad. The building this way is the administration building. That's the vice president's office. Both vice presidents have their offices there. The business office, the records office, the admissions office, all those kind of things, the human resource, they are all in the administration building. No classes at all. The long building on the back side, perpendicular to that, that's the B building. Okay, so A building, the B building. It's called the academic building. Okay, now it has 2 floors. There's the ground floor, and then there's the main floor. I'm on the main floor. When you go on either end of the building, you either have a choice of going down half a flight or up half a flight, go up half a flight. If you come in the side of the building toward the student center, toward Winona schools and stuff like that, you have to go all the way to the end of that building. Just before you hit the stairs to go down, last door on the left is B122. Ask anybody there, Dr. Pruitt's office. I'm not Dr. Pruitt, he's my boss, okay? But he has a little copy room in his suite of offices, and that's where I am on Fridays, okay? If you come in from the baseball field, the tennis court, the gym side, in that, go up half a flight. When you hit that last step at the top, immediately on your right. That's room 122. And when you go in, the secretary is right there in front. Her name is Miss Rose Saxon. My little room is right behind hers. He's got the corner office, of course, but I'm right next to his in the copy room. Okay? Now, so that's where I am on Fridays. My office hours. On Mondays and Wednesdays, I have a short amount of I have an 8 o'clock class, a 9:30 class. A 9:30 class is a calculus class, and it goes until 11:10. So I'm trying to be in the office between 11:15 and 12. Okay? Only 45 minutes, so it's not much time. And I try to eat lunch then, but I don't mind you coming by if you need to see me 11:15 to 12. But then I have a 12 o'clock, another calculus class, and then I have a differential equations class, and then I'm free from 3:15 to 5:15 every Monday and Wednesday. That's the best time to catch me on Monday and Wednesday, 3:15 to 5:15. This is so short, and I try to get lunch, and I try to, there's not much time here, but I've got 2 hours there. And quite often I'm here after 5:15. Not always, but sometimes. Like tomorrow, if I'm going to that movie, I'll actually have to leave early. Okay? Tuesday, Thursday, I have an 8 o'clock class and a 9:30 class, but that's only a trig class, so it gets out at 10:45. So I'm back in the office usually between 10:45 and 1:15 when this class starts. And then after that, we're here the rest of the day. Okay, so those are my office hours. All these are on Bessemer campus. Then on Fridays, I have no classes. So I'm in the office from 7:45 to 1 o'clock with one really big exception. Well, actually a couple of exceptions. The exceptions are they love calling meetings on Fridays. So if they do, then I may be in a meeting. If I know about it ahead of time, I'll let you know by Thursday what hours I'll be out of the office. If they spring it on me when I get there on Friday morning, then I won't know. So if you call and I'm not in the office over and over, wait maybe half hour to an hour, and then try again, because it may be I'm stuck in a meeting, not in my office. Okay. So 7:45 to 1, I'm there. Most of the time I'm there after 1, Usually not too late after one, because by Friday afternoon I'll be okay. Because I'm here till 5:15 on Mondays and Wednesdays, 5:45 or 6 o'clock on Tuesday and Thursday. So I'm usually spent by the end of Friday. Okay, course description. Now, this is not something I made up or anyone here at the campus made up or anyone in any of the two-year colleges or four-year colleges. This is something a committee got together from the public four-year schools in Alabama and the two-year college system and said, if we do this, they give you credit for it. This course provides the non-technical student with an introduction to basic principles of chemistry and physics. Laboratory is required, so we will have labs. I will talk about it in a little bit later. Now, this we can't change because this is done by the state. But what we can do is how we do it, okay? We're going to do physics first and then chemistry. Because like you saw, now you're not an automotive student either? Okay. All those guys, but not her either, okay? All these guys, and there were a bunch in here, I don't know if you saw them, they are, I think, mostly Ford students, okay? And that's why we start at 1:15, because they're in class until 1, and they need this to graduate. So I scheduled this for them. That's why it's on second mini-term, because the way our automotive programs, or at least 3 of the programs do, they're working half the term and they're on campus half the term. First-year students are on campus the first half and then working the second half. Second-year students are working the first half and on campus the second half. And these are second-year students. They've just gotten back from their work this week. So that's why they're here, and they had to go there. And one of them has National Guard or something, Air Force or something that he has to do in Mississippi on Thursday. So that's why he won't be here. But anyway, but most of them are automotive, so I think they need the physics more than they need chemistry. So we do physics first part and chemistry at the end. All right. Prerequisite, just whatever is required by your program of study. The only thing that you really need much of is math, and not a lot. If you've had at least math of 098 or higher, you're fine. Even if you haven't had 098, more than likely you can do all the math that we're going to do in here. It's pretty simple stuff, okay? As it says, non-technical students, okay? So no calculus, none of that kind of stuff. Not even very hard algebra. We'll do a little algebra, not a lot. Co-requisite, none. The textbook, and as we talked about before, one of them asked before they left, and one of those guys is an automotive too, I remember, is this book. It's Physical Science by Bill Tillery, and it says 10th edition here. Now that little book that he had, and that's what the bookstore had, and I don't know if you're familiar with these. Here's Terry. Okay, good deal. Now, how did I come up with my pen? Did you have it? Okay, I knew I had a pen in here. All right, Terry's here. We have Brittany Terry and Terry Wright. They do that at the end of the alphabet. Okay? But this has never happened to me before. Okay? Now, on my Tuesday, Thursday pre-calculus algebra class, I have 3 A. Joneses right in a row. Amber Jones, Alyssa Jones, and some other Jones, but they all are AJs, okay? But they go by the first name. But in this class, and they sat here, here, and here, or something like that, I had a Jacob Camp, a Jacob Collier, and a Jacob Daughtery, all right in a row, and they all went by Jacob. Until they said, no, we call each other Camp and Slim and Dart, okay? So I've never had 3 Jacobs in one class before. I've had Jacobs before, but never 3 at once. Okay, so Terry's here. And by the way, I've had Brittany Terry and Terry Wright both in other classes before. That's why they know me. Okay. So the textbook is either this one or that little textbook that you saw. I can't remember his name now, but the guy that was sitting right there had. Either of those is fine. Now here's what I was starting to say. I don't know if you're familiar with how they do textbooks, okay? They come up with new editions about every 3 or 4 years, and hardly anything has changed. And you might say, why would they waste the money doing that? Because they want to make money. Because you see, the book publishers only make money when you buy a new book from them. If you buy a used book from someplace else, they don't make any money on it. So therefore, they make their authors change the editions every 3 or 4 years so they can sell more new books. So this is 10th edition. The one that he had is probably 8th or 9th. Who cares? The physical science, most of the wording has not changed. Most of the figures have not changed. Maybe a few questions have changed, but it's all the same physical science. That hasn't changed. So I let you use any book that you have, and that will get you buying anything. So any book they have in the bookstore will work. The little books, what I was going to describe there, the publisher at one time was really hot on customizing text. In other words, he said, well, which chapters do you need? What do you teach from? I said, for this class, I teach from chapters 1, 2, 3, 4, 6, and 8. Okay, we'll just bundle those together and sell them much cheaper to your students that way. Sounds good to me. The other class, we use chapter 14, 15, 16, blah, 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 blah. So I just gave them those chapters, and then they published those together. So it saved the students money, and that's why we did it. Well, because that was what we do, our bookstore couldn't sell them back anywhere, so but they would buy them back from the students, so they've resold those books ever since, okay? Because we're the only ones that use them, because we're the only people that only use those chapters. And in fact, if you look at that book, it says my name on the front, because I'm the one who said this is the ones I teach from. I didn't write that book. Bill Tillery wrote it. They just pulled out those chapters. It's called customized publishing. They don't seem to like to do that anymore, but for a while the companies were experimenting with it, so that's why some of those books are available. That's all you'll need. Now, they did a few things I wish they had done differently, but they didn't run them by me, so I didn't know it until later. So if you have that book, that's fine. Students are expected to bring the textbook, paper, and pencil or pen. I don't care if you use pencil or pen. It's just when I do math problems, confession time, I tend to make errors. So I like to use pencil, okay? But if you're happy with pens, you can do that. I don't care. And why do I say bring it every time? I teach from the book. And we work problems from the book. So that's why I bring the paper and pencil. Calculators are permitted. In fact, I would say encouraged in this course. And all you need is a simple little calculator. Add, subtract, multiply, and divide. That'll get you by everything you need to do. If they can do square roots, that's fine. We may do a few of those, but not many, okay? If you already have a scientific calculator, more than you'll need, but that'll be perfectly fine. If you have one of the big fancy graphing calculators, fantastic, fine. You won't need it, but you can use it. Don't buy a new calculator just for this. So calculators are permitted. And by the way, I put on my book orders every time, when I order the books, I put calculators are required. So if you got Pell Grant and you want to buy one on the Pell Grant, you can, because that's on your book order. If you already got one, you don't need to take the money home. All right, now this next paragraph I found almost ridiculous, okay? They tell us we cannot change this, and this is so out of date, and yet they updated the syllabus and left it the same. All Austin State Community College students must be trained in Blackboard and use Blackboard daily to gain access to vital course information, such as the syllabus. You will read the syllabus every day, won't you? Saturdays and Sundays included, right? Every day you need. No, I'm making fun of it, am I not? Yes. Shame on me. Okay. Okay. I'll put the syllabus out there anytime you need it. Go read it. Okay. It's not there yet. Sorry about that. As you see, I've got one fairly minor change I know I need to make, and I didn't get far enough to see if I had any others to change, but I know of one that I need to change. Okay? Now, as I also say, handouts. Now, most of the time, if I have a handout, I'm going to hand it out to you. Okay? I'm not going to put it on Blackboard. I will if you need it that way, but most of the time I don't. PowerPoint shows. Yes. They're not there yet. In fact, I'm surprised they weren't there in that last class. I didn't scroll down far enough to see them. Okay? I will put the PowerPoint for all 6 chapters that we're going to do out there. They're not there yet, but I'm going to put them there hopefully by Friday. I can't swear it. No, it might. Hopefully I'll get them there sometime this week. Okay? I'll put it that way. May not be by Thursday, but I'm going to try to get it there this week. Okay? PowerPoint shows. The only thing, they're going to be there in two ways. First, under that content where you saw me go before, you'll see the static things. You can pull them up, print them off if you need to, whatever you need to do before class if you need to. If you want to just look at them, you can look at them. But the second way is through YouTube. This recording I do, I teach from the PowerPoints. I write on the PowerPoints. And guess what? This is what they call a tablet PC. See, it's not letting me write now, but I bet you I can. Well, I thought I could. Why is my thing not coming up? I don't know. Maybe it won't let me write on the syllabus. I don't know why. Most of the time it does. But on the PowerPoints, I can write. Okay? So, you'll see PowerPoints again. And those PowerPoints, you can hear me talk about, you can see me write, you can see everything on it. So the PowerPoint shows will be in two places, once ahead of time, they're not there yet, but they will be, and then once after we talk about them, they'll be out there. Now, I also didn't say this, I should have back when I showed you that on Blackboard. You saw that the last class, that's from fall, they're there. I'm going to use that same link, that same what they call playlist. So when I do a day here, I'll replace the one that I did then. So guess what? You'll be able to see them ahead of time because you'll have last fall's. You can watch those if you want to too. I don't recommend it, but you can if you want to. They'll all be there. So the PowerPoint shows will be there in two places. Once under content, once under YouTube. Activities. Now sometimes the school puts activities out on Blackboard. Pay attention to it, okay? We don't have that many activities, so okay. Assignments. I will put the paper assignment out there. In fact, it was there on the last one. It'll be there on the new one. I've got to make a couple of changes first before I can do that. Okay? Also, especially at the end of each chapter, I'll go over what I suggest that you study for the test. That's only a suggestion, but you can call that an assignment if you wanted to. So those will be out there. Announcements. Now, I can't think of many times I'll need to put an announcement there, but if I do, I'll put them there, okay? Most of the time in this course, I can't think of any announcements. But if it turns out that I have to have something comes up and I'm going to have to make some adjustment, I'll put that out there. Hopefully not, okay? Grades, especially early in the term, I'll try to keep your grades fairly current, okay? It may be Fridays before I get all the grades in it. That's typically what I do is when I'm on Birmingham campus, all those office hours, I try to get Blackboard and attendance and all that kind of stuff caught up, okay? However, once we start registering for summer and then for fall, I get sort of behind. So then it's definitely going to be Fridays before I get to it. Like today, I don't know how many people came by my office in my few office hours I had, so I got no grading done. My work study student marked a few papers, but I didn't get a chance to put anything in Blackboard then. So hopefully I will. Sometimes on Monday, Wednesday, late in the day, people don't come by as often. And on Fridays, sometimes I can. Usually I get my grades called up on Friday. Okay? I do not like this next sentence. Failure to use Blackboard could severely damage your ability to pass the course. That's such a negative sentence. If they let me write it, I would have said the proper use of Blackboard could greatly enhance your ability to do well in the course. It's a lot more positive statement, I think, closer to reality. Okay? Now, maybe some people teach totally from Blackboard. If so, that might be a good sentence. Okay? I don't know. Now, this next sentence is absolutely nuts. See the schedule book inside cover to determine when you can attend training if needed. We haven't had a schedule book in years. And they don't let us change this. I thought when they made the new update, they'd at least take that sentence out. They haven't. If you need help with Blackboard, see me. I may not be able to help you directly, but I can find somebody who can. Someone who knows it really well. Okay? See, I know the instructor side. I don't know the student side as well. Okay? Students should always check Blackboard announcement page prior to coming to class. I kind of resent that statement. Why would that be in there? Why does it tell you that you should always check Blackboard announcement page prior to coming to class? What's implicit after that? in case the instructor has canceled class. Guess what, folks? I'm going to be here. I'm a full-time instructor. I'm always here. If I get seriously ill or something like that, the odds are I'm not going to have a chance to put it on Blackboard. I'm dying here. No, yeah, I'm probably not. If I know about it ahead of time, I will have already told you, okay? But if something does come up that is completely unavoidable, I'll put it out there. But don't expect much from me for that, because I'm going to try to be here. Even if I'm coughing, sneezing, whatever, I'm going to try to be here, okay? Just about always. Let me see if I can delete that line there. Okay, now, here are the core student learning outcomes. And by the way, do either of you have your books? Not yet? Okay. I told you what we'd be covering. And by the way, let me say this to you. Just about every physical science book that I've looked at and reviewed and considered, they always do physics and chemistry at the front in that order, whereas our course descriptions say chemistry and physics. So I do it the way the book does. Then they do astronomy and earth sciences last. Okay? But if you notice, this is physics 2, physical science 2. Physical science 1 was astronomy and earth science. Exactly backwards. Alabama does it the reverse order, and the books are written in the opposite order from that. So we're at the beginning of the book, even if we're physical science 2. I just finished teaching physical science 1. Brittany was in that, so was Terry, and we did astronomy and earth science. So we started at chapter 14 and went through 30 to 24. We'll start at chapter 1 and go through 8, but we won't cover them all. So what I was going to say is, if you look at this, next to this, it says students will describe student learning outcomes. Students will describe the nature of science, identify quantifying properties, use measurement systems, calculate densities, identify laws, principles, models, and theories. Chapter 1, what is science? Objectives and properties, blah, blah, blah. Basically, that's chapter 1. Chapter 2, student learning outcome number 2, students will solve problems using basic principles of motion. Chapter 2, motion, okay? Student learning outcome number 3, students will solve problems using the basic principles of energy. Chapter 3, energy, okay? Number 4, students will solve problems using the basic principles of heat and temperature. Chapter 4, heat and temperature. See, it goes right by the book. Number 5, the students will solve problems using the basic principles of electricity. Well, unfortunately, chapter 5 here is waves and sound. Okay, wave motions and sound. That's a great chapter, but I found we seldom had time to do it. And I thought, especially for the automotive people here, what are your majors, by the way? Welding? Second, automated manufacturing. Okay, I'm guessing you use electrical stuff more than you use wave motion and sound. Would I be right on that? Okay, I figure most people do. So we skip and do electricity, which is chapter 6. And it shouldn't just say electricity, it's electricity and magnetism. Okay? And then chapter 7 is light. Again, a great topic, interesting topic, but we got to have some chemistry in here. So we jump in next to students will solve problems using basic principles of chemistry, and chemistry's first chapter, and the only one we really have a chance to do is chapter 8, atoms and the periodic properties. First chapter in chemistry. Because I figure most of the students, mostly those automotive students, they need to know about motion and energy and that kind of stuff. And most of our other majors do too. So that's why we did that. Number 7, students will write a library internet-based research paper. We'll talk about that next. Okay? But that is required for the course, the way I teach it. Not everybody teaches it this way. Number 8, students will conduct laboratory experiments and write the results. I will give you the things you fill out mostly on the paper. Okay? It's not as bad as it sounds. Okay. Now, those are the student learning outcomes. Here is the competency guide sheet. Goes straight by that. Remember, this was chapter 1. Chapter 1 has one laboratory assignment, and then we'll have a test. By the way, that one laboratory assignment, first chapter, shortest chapter we do, it has the most complicated lab assignment. So that's this first lab, you'll say, oh no, I got to put up with 8 weeks of this. No, this will be the most involved one that we do all term. They kick it to you right off the start. The rest of them will be a lot easier, a lot shorter, and I think a lot more fun. Though this one isn't bad, but it will only be one. Then when we do the principles of motion, we'll have either 2 or 3 lab assignments for that one, and then we'll have a test. If we were on full term, we probably would have 3, but on mini term, we just get so crammed with time. Okay, students will solve problems using the basic principles of energy. Again, either 2 or 3 for that one. Students will solve basic principles of heat and temperature. Again, 2 or 3 here. Yeah, 2 or 3 here, and 1 test then at the end. Electricity, again, 2 or 3, and the test. Chemistry will only be 1 again. We only have time for 1. And we really don't have a big chemistry setup here, so it'll be pretty much a paper one, and then we'll have the test on that. And you will write a internet-based paper, so your research paper is one of the competencies, and then you'll have a comprehensive final exam that covers all 6 chapters. Okay? Don't sweat that. That'll probably be the easiest test we have. Okay? I just take the major points from each of these, like 2 or 3 of the major topics, put them together. It's a pretty easy test. Okay? So don't sweat that, but everybody has to take it. So how will I evaluate you then? Following this is the breakdown. They put these words in here. I think this is really redundant. Of how each student will be evaluated for the final grade calculations at the end of the term. The research paper is required in the way I teach the class, required for the class. That means it's not optional. You can't substitute a test for it. You can't do anything. It's required. Okay? Meaning if you don't do it, that's a 0. Okay? Sorry about that. Do it. Okay? And again, it's not really as bad as what it may sound. The guy that was leaving said English 101 is not as involved as one of those papers. Okay? It will count as a test, but that one cannot be dropped. The research paper cannot be dropped. Now, chapter tests will be given at the end of each chapter. 1, 2, 3, 4, 6, and 8. Okay? So that's 6 tests there. I'll say this, I may drop your lowest test score. Now, why do I say may rather than will? What if you don't turn in a research paper? Or you do really poorly on the research paper? Or maybe you don't do the final, or you do really poorly on the final. Those can't be dropped. If you need those tests to bring up your score, I count them all. Okay? If dropping one brings up your score, I drop it. So I do whatever it takes to bring your score up. So I only drop 1 test. That's one of the chapter tests. Okay? There will be at least 1 laboratory assignment for each chapter covered. Most of them will be 2 or 3. Okay? The first and the last chapter, 1 each. The others, 2 or 3 each. Okay? The lowest lab assignment may be dropped for the same reason as before. If it helps your average, I drop it. If it hurts it, I don't drop it. Okay? So a laboratory grade will be averaged from the remaining laboratory assignments. And the laboratory assignment now, let's go back. Think back of what we saw earlier. 3 credit hours for the theory, 1 credit hour for lab. 4 credit hours, 1 for lab, so I'll let the lab be a quarter of your grade. The test and everything else are 3/4 of the grade. So what I do, I'm really lazy, if you'll learn this soon enough, I make all the lab scores out of 25. So all I do is average the lab scores after I drop the lowest one, average those together, that's 25 points. Then when I average all the other things, we'll get to that in just a second, the average of the paper that can't be dropped, the remaining test scores after I drop the lowest one, if that helps you, and the comprehensive examination, which cannot be dropped. Okay? So, no, okay. I can hear it now at the end of the term. I have all A's on my test. Does that mean I get to drop the final? Can you answer that? No, you can't. It's required. Comprehensive final exam cannot be dropped. Okay? So, when I average those together, those are out of 100. Then take 75% of that, or 3/4 of that, add to that your lab average, that gives you your 100 points. Okay? The comprehensive final exam cannot be dropped. So don't come asking at the end. By the way, you don't want to. It's probably going to be the best score you made. Okay? May not be, but I think it will. And then you know how this grading goes, don't you? Any 90s or above are A's. Anything in the 80s or B's, 70s or C's, and don't go down here. Don't get into D's and F's. You don't want to be there. Okay, attendance. You're expected to attend all classes for which you're registered. If you can't attend the class regularly, now the guy that was sitting over here, can't remember his name now, I don't think he was one of the Jacobs. Yeah, he was. He was the first Jacob, wasn't he? Okay. He has got a developmental math class, or maybe it's not developmental, it's maybe Math 100 in the evening, okay? And because he has it in the evening, and he said he thought it started at 5, he's going to have to leave early. So he's going to have to make up any time that he misses here. The guy who's sitting there, he's going to be going to Mississippi on Thursday. He's going to have to make up anything he misses there. So, yeah, I understand life gets in the way, but please, if you can be here, even though I'm recording this, even though you'll be able to see it later, right, Brittany? It's not as good as being there, is it? Okay. She's had to make up something from the last class. She didn't want to, but only way she could do it. So, she had to listen to me several times. Okay. What a pain. Okay. All right. If you can't be here and it's going to hurt your grade, consider withdrawing rather than hurting your grade. Now, remember this about withdrawing. The good thing is it doesn't hurt your grade point at all. There's no penalty for withdrawing. If you withdraw in time, you'll have to check the academic calendar to see when that time is. But if you make a D or an F from poor performance, that hurts you because it hurts your grade point average and everything else. Now, the only negative thing about withdrawing is, now this is assuming that you're on Pell Grant or some other kind of assistance. If you're on one of those programs like that, usually they will let you retake a class once. Say you made an F, a D, or withdrew, you can retake it and they still pay for it the second time. But if then you make an F, a D, or withdrawal the second time, they won't pay for it the third. Okay? So don't even go there. But guess what? The only time I would ever suggest that you withdraw is if you're in a danger of making a D or an F. And if you're in danger of making that, if you don't withdraw and make a D or an F, they're not going to pay for it the next time either. And that way it hurts your grade. With a withdrawal, does not hurt your grade. So I have one student in my Calculus 1 class who's withdrawn from Calculus 1 twice. Okay, this is the third time taking. I don't think he's on financial aid. If he is, they're not paying for it. He's having to pay for it out of pocket. But it was better than getting a bad grade. Okay, so not a bad move. Okay. I don't think any of you are in nursing or allied health programs, so you don't have to worry about that. But if you're going, before you withdraw, see your advisor, check with financial aid, find out all the ramifications. In general, it's always better than making a D or an F. If you're withdrawing because you didn't want to make a C, now that may be a little shaky. Because C doesn't hurt you, you pass the course, you move on. Withdrawing, you have to repeat the class. You don't withdraw. Okay, makeup work. Laboratory assignments, try to have them in within a week of when we were finished them. If we do start the first lab today, which I don't think is getting less and less likely we're going to make it today, but if we do start it today, but don't finish it, then we have to finish it on Thursday, then you have a week from Thursday. So it's not from when it's, this is a little bit bad here, from when it was distributed, after they distributed, no, after they're finished, okay? But I didn't want to put finish, so you might say, yeah, but I didn't finish it. I'll finish it next week and then turn it in the next week. No, that's not what I mean either, so okay, that's why I said that. If a student cannot make the schedule, please contact me and let me know why, and then we'll try to make it up. If a student has to miss a scheduled test or lab, then the student has 1 week. Try to get those made up within a week, okay? Now, let's say that guy who's going for some sort of military thing, I think it's physical and that kind of stuff to go in, okay? Well, if it's National Guard or something and he winds up having to go on 2-week training, we're not going to penalize him for that. So yeah, he's not going to be able to make it up in a week. But when he gets back, he's got a lot to make up. But we work with him and try to help him as much as possible. Okay? And sometimes if you get your flu, you're not going to be out for more than a week. Okay? So we work with that. So try to work with me. Let me know, and we'll work with it. Lateness, all classes except today. We're going to try to start right at the scheduled time, 1:15. Now, if those guys are over there and they get held up in lab, they may be a little late getting here. If I get like today, goodness gracious, all these people coming by my office, I was not late getting here, but late getting set up. I'll try to be here and be ready to start at 1:15. So try to do that, okay? Students who miss work because of lateness will not be allowed to make it up. Wow, I'm pretty easy that way. Okay. And students who come in late will not be allowed additional time to complete tests or other assignments. Most of the time, I give you whatever time you need. I'm a lot more interested in measuring what you know than the other thing. So try to be here on time. Now, statement on harassment, discrimination and harassment. Let me summarize this for you, okay? We don't tolerate it. We don't condone it. If we hear about it, we deal with it. We deal with it quickly but fairly, and we don't want it happening on our campus at all. And I've been here, can't remember if this is my 19th year or 20th year, something like that, teaching mostly from this classroom, not always, mostly from this classroom. So I've seen a lot, back when we were Western State Technical College, and now that we've been Lawson for most of that time. And frankly, I have seen little that we classify as discrimination or harassment, and we want to keep it that way. But now, that's not guaranteeing that it hasn't happened. Maybe people are doing it and being very clever and not letting us know about it. But what we ask of you, if you see it, sense it, even have a suggestion of it, maybe it's not yourself or somebody else, let us know, because we don't want it to happen. We want to nip it in the proverbial bud, okay? Now, the closest thing I ever remember, this was back when we were at Western State Technical College. I was teaching the automotive students, the automotive math, we called it back then, vocational technical math. And it was one of the first 2 or 3 years I was teaching here. And I don't know if you noticed about these students. Some of them look to be more like your ages. I'm assuming y'all are sort of non-traditional students, is that right? Or are you fresh out of high school? Somewhat fresh, okay.
I'm almost graduate.
Okay, say again?
I'm almost
okay. Okay. Been out a while. Brittany?
Oh,
Fresh out of high school?
yeah.
Yeah. Okay. So we have some. Usually it's about 50-50. But with these guys, I've had some older students in the automotive programs. But a lot of times, these are right out of high school. And, yeah, and not only that, they really didn't like high school very much. They like working on cars. They don't like being in class, okay? Y'all probably were much better students in the regular classes. Now, that's not to say these are dumb guys. In fact, I've had some really, really sharp guys here. They just like doing things with their hands rather than sitting in a classroom. But one of those early times, we had this kid, and he was immature for high school. I think his father made him come. He wasn't even interested in doing cars, but he said, "You got to do something, son." I'm guessing on this. So he was here, but not really here. And one day, after lunch, he decided to walk across the cars in the parking lot, from one hood to another hood to another hood. I didn't see it, but I heard about it. And the dean heard about it. He was yanked into his office, and I'm sure given a fair hearing. He was off campus, and I've never seen the kid again. I mean, he was not to be here, to do that kind of stupid stuff. Now, that wasn't really discrimination or harassment, but to me it falls in almost the same category. Now, I'm not saying he didn't get a fair hearing, but he shouldn't have been here in the first place, and he was out of here, okay? Now, we do give people, if you want to file a harassment complaint, even if it's against me, we will help you do it, okay? I mean, it sounds stupid, but we will, okay? Contact us. We will help you with the process, okay? Harassment of any kind, of any nature is never tolerated. The college takes such charges seriously. You read up here, any practice or behavior that constitutes harassment is a violation and will not be tolerated. Get the idea? It will not be tolerated. We deal with it quickly. So please let us know if you even have a hint that's happening. This includes things like bullying. If you see someone being picked on, please let us know. Don't want this to happen. Okay. Now, this part here is going to be changed. This is the one part I know I've got to make a change on. Okay? Americans with Disabilities. Just in the last month or two, the school found out that it's a new statement that we didn't have in our syllabus. It says the same thing, but it says it a little bit differently. So they wanted everybody to go in and change it. That's what I was doing before I got interrupted the last 3 times in my office. I never found the correct wording to put here. I thought I had found it, but it was an email referring to it, but not the one with it. So I've still got to change this one, but it says the same thing. Basically, American disability is the law. Just like discrimination and harassment. That's the law. This is the law. If you have any kind of disability, for instance, I'm hard of hearing. You've already heard me have to ask people to repeat names and stuff like this. I can't hear well. So I'm pretty sensitive to disabilities because I have a very minor one, but I still have it. So please let us know. We want you to learn, and we want to overcome whatever we need to do to make it easier for you to learn. So if you need accommodations, let us know. Now, it doesn't do you a lot of good to tell me. You can tell me. I'll send you right down to Dr. Herndon because she's the expert on it. She knows this stuff inside and out. She's the ADA representative for the whole college, and she's here on this campus, Dr. Renee Herndon. There's a phone number, and she's here. Now, this is the thing I need to change. It's now a Miss McCoy on the Birmingham campus, okay? I have her information, but this is the old syllabus, so I don't have it on here. And the phone number's changed, too. As soon as I get that change done, you'll have it. I'll put that out there. If you are an ADA student, it's your obligation to present to us. I have actually had students I've seen, and they sit in the back of the room and squint like crazy. I know they're having trouble seeing. I can't say to them, are you blind? No. Or even, do you have trouble seeing? Would you like to move up? Because right then I've discriminated against them because I picked them out and said that. Can't do that. I can't. So please, you have to let us know. Okay? I had a student last term, first mini term, in a wheelchair. We couldn't use this classroom. He couldn't get up the stairs. We have lifts at either end, but his wheelchair was of such a shape it wouldn't fit on the lift. Okay? So we moved down to another classroom. So I didn't teach physical science here. I taught it down on the main level where he could get around. Okay? I've had a student who had a brain tumor that when they did surgery, they messed with his hearing. They cut a nerve that affected his hearing. He set his recorder up here on my desk, and I taught with it. He got it home and cranked that baby up as loud as he could so he could follow everything we did in class. He was a good student, by the way, too. So whatever it takes, let us know. We will try to accommodate. So, but it's your responsibility to let us know. Now, oops. Okay. Now, try to get the paperwork done early in the term so we can start the accommodation early. All right, here they are back. She stole your seat, okay? So, okay. In fact, she sold several seats now. Okay. All right. Okay. Going over the syllabus, we had a few other things to do. You'll be able to follow it on YouTube, but it won't be there tonight because it takes a long time for it to upload. I'll try to get it there tomorrow evening. Okay. Try to. Things took longer today. We're talking about Americans with Disability. If you have a grievance that you don't think you've been given a good hearing, we'll help you write us up, okay? We'll help you put us on report because there are procedures you go through. We'll help you do it, okay? And we want you to have a fair shake. Now, the college or academic calendar is out there. It says posted via Blackboard. It's out there on the website. This is old. It should say website. If you go to the website, on the main page, those tabs at the top, one of those tabs says academic calendar. You can see all the dates of importance there. And I think Mr. Harris did want me to point out, I think you'll hear from him, there's a faculty meeting, not this Thursday, but next Thursday. Okay? When I get notice, in fact, I just saw the notice came through that they changed the dates on it. I will send it to them and say, look, I've got a second mini-term class. Some of the students already had to miss part of one class because of graduation. And, this is a week's worth of material we'll be missing. They'll say, fine, meet your class. So I won't go to the faculty. I will sacrifice the faculty meeting just to be with you guys. I mean, can you expect much more than that? I mean, oh, wow. No. For you, anything. Almost. Okay. All right. So, anyway, you'll see that out there. Also coming up this term, I think on a Thursday, is the Honors and Awards Day, but it won't affect this class because it will be in the morning. But check the academic calendar. On that, you'll find things like last date to withdraw and that kind of stuff. Not that I think any of you will need to, but all those important dates are listed on the academic calendar. Okay. Once I get this corrected, now this was the one I used last fall. I got most of the corrections made, but the one thing, the Americans with Disability, which we were just finishing, they've changed some wording on that. I'm going to go back and get that corrected. I was doing that over lunch. I thought I'd have plenty of time to do it, and I had about 3 or 4 interruptions between that and the time class started, so I never did get to make that change. But the rest of it, I got changed. Once I have it out on Blackboard, I'll let you know. Then you can either print this page, sign or type your name, write or type the date, and turn it in to me, or you can type it in and extract this page and email it to me, whichever you want to. But it's not there yet. It will be on Blackboard. I can't say when, but it'll be soon. Okay, hopefully before the end of the week. I'll let you know on Thursday whether I got anything done. I know I won't be able to work on it this evening, and not much anyway. Possibly tomorrow. Tomorrow I've got office hours from 3:15 to 5:15, but I'll announce this to the rest of the class, but y'all are already gone. Y'all know the movie Hidden Figures? Have you seen it? Okay. It's out of the movies now, I think, but UAB is going to be showing it in their student center tomorrow evening. It says 5, but they're showing it now at 6, but try to be there by 5:30 because finding parking on UAB campus is not easy, okay? So if you can carpool together or something like that, it's free, and I think I heard that they're actually going to have a cast member there. If you don't know where the University Hill Student Center is, I can explain it to you. Does anyone need directions? It's real easy to describe. Okay. If you do, see me. I'll get you there. Great opportunity. So if I make it to that tomorrow, usually I'll leave at 5:15. I won't be able to leave at 5:15 tomorrow because I won't get there in time. I'll probably leave early. So, but other than that, I'm usually there here until after 5:15 on most Mondays and Wednesdays, and here till probably 6 o'clock on Tuesday, Thursdays. But my office hours, I have so few office hours. Thursday, I'll try to get these finished on Thursday if possible. What's that? No, well, it wouldn't be a bad idea to take your Lawson ID. I don't think it's necessary because we've been invited to just tell them you're from Lawson State. But it's not a bad idea. I hadn't thought about that. It would be a good idea to bring your ID. Okay. In fact, it's always a good idea to have your ID available. Okay, so that's the syllabus. I know y'all didn't hear most of it, but I've been recording so you can pick it up when I get it out there on YouTube. But that takes a while because after class, it starts uploading. I'll leave it uploading overnight. It doesn't take that long, but I'm not going to stay here until it finishes because it takes hours. Then tomorrow I'll be in class all morning, so it'll probably be tomorrow afternoon before I get it into the YouTube on the playlist. and I still got to move the playlist to Blackboard. I haven't done that yet, but it's pretty easy to do.
Have
So.
you already went over our tests? How many tests and quizzes?
Yeah, no quizzes. It's going to be 6 tests. You got a research paper, which we're going to talk about next, 6 tests, a bunch of labs. The first chapter, 1 lab, the last chapter, 1 lab, and the other chapters either 2 or 3 each, okay? And a test after each chapter, and that's going to be the grade. So yeah, all that will be there. As soon as you can access it, you can hear all that.
Do you have any homework?
Okay, most of the time the homework at the end of each class, I'll let you know things that you need to do. Most of the time it's read the chapters. Read the chapters. Right before a test, I'll tell you the best things to study for the test. I'm going to make you study them, but that's up to you. But I'll tell you the good things to review and go over for the test. And then we'll have the labs, and sometimes you'll probably take some of the labs home and work on at home, especially this first one, and maybe some of the others too. So there'll be those kinds of things. But most of the time, there's not any assigned homework, it's just stuff that will help you do well in the course. Okay? All right. That is the syllabus. So let's end the syllabus. I think I made one change, so it's going to ask me to save. I meant to put the save button, but I didn't, so I'll catch that in a minute. All right, let's get out of this, out of that, and let's go to the research paper. Most of the time I would have had all this set up before, but like I said, I had so many interruptions. Research paper, I think this is the one. Yeah, I think this is it. Now, it won't be completely up to date. That's why I don't have it on Blackboard yet. I didn't have a chance to make the minor corrections, but I'll go over them now. Okay, the research paper general instructions. You get to choose your topic. I'm not going to assign you topics. You get to choose any topic within the scope of this course. What do we talk about in the course? Physics, chemistry, energy, motion, heat, temperature, thermodynamics, electricity, magnetism. You choose. Okay? Anything that's within the scope of this course. You can talk about a person. I had one student, an automotive student, who was from Croatia maybe, or Serbia, one of those countries, and he was real proud of Nikola Tesla because he came from somewhere near where he was from, and he wrote a pretty decent paper on Tesla, so it can be a person. Lots of people will be hitting every chapter is going to focus on some person. Okay, we'll talk about that a little bit later. It could be a theory, okay? For instance, Maxwell's equations, or something like this, the theory of atomic theory. We're going to hit that in several chapters. Okay, any theory like that you might choose. A phenomenon, okay? This is especially easy in my first course in astronomy, like the Big Bang Theory or the a supernova or something like that. But anything like that in electricity and magnetism. Oh, photoelectric effect, okay? Diodes, okay? You use dual diodes as what used to be your alternator. Now you use dual diode system, right? To take the AC current that your generator makes and make it DC so it can recharge the battery, right? If you want to write on something like that, that's good. That might also be an application, okay? I had a Ford student one time, I'm trying to think, I believe this paper was on the EcoBoost system and the physics of that, and maybe a little bit of the chemistry. I had one Toyota student, I think it was, that wrote on regenerative braking, okay? How they use that to do electricity, to talk about the physics of that. So there's lots of application type things you could write on. Any other subtopic about which you have an interest, whether it's your professional interest or just a personal interest. Or, and here's another one, it can be an internet application or a demonstration which you find is helpful in this course. Okay? We talked briefly, just very briefly, about the Van de Graaff generator. I'm not sure it was this course, it may have been a physics course, I think it probably was. And one person found a YouTube video on where this group of people, I think it was from one of those shows, not Mythbusters, but something like that, where the team went out and said, well, let's make us one. And they made a Van de Graaff generator, and they ran into problems and went into that. He found that it really filled in all the gaps. The textbook had a paragraph or two. He had a whole video on it. I said, wow, he got really interested in it. So it could be an internet application or demonstration. Anything that you find either built on this class, comes out of the class, or helps you understand the class better. Huge range of things you can choose from. Now, what I'd like you to do either today or tomorrow, really hard assignment here, write your name on the piece of paper, okay? And the topic that you, at least right now, are thinking of for your paper, okay? And you might say, well, I've just begun to think about it. Well, that's what I'm trying to get you to do. Start thinking about what you'd like to write on. So either today, if you know already, or Thursday, if you can figure it out by then, something you like to do. If you need to change, you can change. But get an idea rolling. Guess what? 8 weeks is all we got. Okay? If you put it off and start thinking about it in week 7, you're going to have a hard time getting a good paper written. Start thinking about it now. We'll talk about this a little bit later too. So try to do that today or Thursday. Okay? And return it to me. Now, that's an awful little to put on one piece of paper. So let me give you an option that has nothing to do with this. If, in addition to those two things you want to put on the paper, you don't have to do this, but if you choose to, you can. If you want to write down your very best phone number, in case someone's trying to reach you. Now, the odds are I won't be trying to reach you because I'll see you, okay? But periodically, it doesn't happen frequently, but it does happen occasionally. I'll get a panic phone call, maybe over lunch, on a Tuesday or Thursday, from some office saying, thus and so's in your 115 class. Do you have a way of getting in touch with them? Or maybe it's on a Monday and Wednesday. Say, we notice he's in your class, or she's in your class. Do you have some way of getting in touch with them? The number in our system's wrong, or we can't get through. Do you have a better number? So that's why I'm asking you this. If I don't need it, I'm not going to use it. And if they never call, it's just going to get destroyed at the end of the term. But I'll have it in case they need it. Okay? You don't have to give it to me. Now, if that very best phone number, I'll bet you right now, is going to be a cell phone for most of you, right? Well, what if you lose the cell phone, it gets dropped under the jack at work, or in lab, or you left it at home, the battery died or something like this, and you can't be reached. If you want to give me a good backup number, in other words, Mama's landline or something like that, if you want to do that, you can. You don't have to. But if you want to give me a good backup number, you can. And the only third option I can think of, and you don't have to do this either, if I have a feeling some of you probably go to work, maybe on Fridays or sometime like that, maybe after class, I don't know. But if the place you're likely to be when we're trying to get in touch with you is work, and you can receive a phone call at work, and that may not be on the records down there, and you want to give me the number, you can give it to me. Like I say, I'll probably never use it, but only if someone official from the college, I'm not going to give it to anybody, has to be someone here at the college who desperately needs to get in touch with you. If I have it, I assume when you give it to me, you'll let me give them to you. Not just any Joe Blow that comes in, like, I'm a collections person, I need to know their number. They're not going to get it from me, okay, because of privacy issue. But if it's somewhere here at the college, I will. So if you want to put your phone numbers there, no phone number 1, 2, or 3. I can't think of any reason I need more than 3. But you can give me none or any one of those, or 2 or 3 of them. You can. Okay. Since you're going to use the whole piece of paper for that. Okay, now, you will need to find at least one, but 2 or more are better, outside sources for your paper. Now, what can they be? It can be from any book, journal, articles, newspaper, magazine, anything that you can find in the library, either our library here, county library, city library, something like that, anything you can find there, or, now, I hate to do this, and a lot of people don't, any legitimate source. Now, underline and put this in bold, legitimate source found on the internet. I tell my classes this, and it's unfortunately more truth than it's funny. The internet has to be probably the greatest invention that's happened during my lifetime. I was born in 51, okay, and I don't think it had started then as every bit of it's been developed during my lifetime. And it is incredible. It is amazing, okay? Two big problems with it, though. First, I bet you at least, and probably way more than half of what you find on the internet is total garbage. Second problem is sometimes we can't tell which half, okay? So be careful what you use off the internet. Make sure it's something that is legitimate, okay? If you have any question about its legitimacy, ask me. I'll take a look at it, and I'll probably be able to pick out and say, no, that doesn't quite seem like, oh, yeah, that looks like a good source, okay? But you can probably figure it out, too, okay? Now, like I said, every chapter has a blurb, a pretty extensive blurb on at least one person, and sometimes many names or other things. The book can't be a source. The book could be a source for an idea, but you're going to have to get your research from something outside the book. That's the whole purpose of this, get you out of the book, out into the real world, even if the real world is just a library, okay? Get you out there. So that's, you can get the idea from the textbook, but that can't be your source, okay? Your paper needs to be at least one word process page of text, okay, at least, okay? Now, word process means I don't want a handwritten paper. Don't even try it, okay? Word process. You've all had English, right? You had the word process in that, right? Okay, one more. Okay, please do it. Okay? Now, what do I mean by word process page of text? Now, let's just imagine, I say a lot of papers come in, and a lot of them have a header up here. I don't require a header, but if you want to do it, you can. If you put a big header here, triple space, then put the title in triple space, and then start typing here, one page of text is going to go to the bottom of this page, and then on the second page, come down from the top, past all that stuff, and go at least that far. That's a page of text. Not one piece of paper, one complete page of text. That's the minimum. You can go more than that if you want. And by the way, I'll let you double space. In fact, I want you to double space. This is single space. If I were correcting this, this would be hard to correct because there's not much room to write in there. Double space, so you get half the number of words I got on this one, okay? Sort of, okay? And I want the standard font. I don't want any 26 font so that 3 words fill a page and you say I'm through. That's not going to work. Nor do I want any 9-point that I can hardly read. So try to have the standard sort of 12-fit, 12-point. That's what I've got here. Okay, the font you use is completely up to you as long as I can read it. I don't read hieroglyphics or Old English or Greek or Cyrillic or any of that, so don't try that. You wouldn't think of that, would you? Okay, so use one of the standard fonts. Most of the defaults are Times New Roman, okay? I happen to put this in Arial, Courier. I couldn't name them all. There's tons of good readable font. Make sure it's something that's easy to read. Try to keep the paper less than 2 pages. Now, that's not a hard and fast requirement, but I want it at least 1 page. Try to keep it less than 2. I'm not trying to get you to write a dissertation or a thesis or something like that. I just want you to get out of the book, into the real world, and show me that you've done some research. Just a little bit, okay? Now, you'll lose points if it's too short. I don't take off points if it's too long. If it's more than 2 pages, I've had some great papers that went several pages. The student got so interested he just couldn't stop, or she couldn't stop. No problem. I don't take off points if it's too long. But let me tell you this. This is how I grade the papers. When you turn it in to me, it's a 100-point paper in my mind. And then I start reading it. And I can hear you now, don't read it. No, I'm going to read it. And as I do, if I find errors, you start losing points. Okay? Now, if you are careful and do a good paper, you're not going to have any problem that way. But if you're trying to replace quality with quantity, it's not going to do you any good. You say, well, I'm going to jot something down here, but maybe if I give them an extra few pages, it'll give me more points. Well, if it's a sloppy paper, it's just going to keep losing points and losing points and losing. It's not going to do you any good at all. Okay? In fact, it may even hurt. So, try to keep it less than 2 pages, but I don't take off if it's longer. Okay? Now, You can use any standard format for the paper that you choose. If you've had English class, I bet you've learned AC, what do you call it? MLA, Modern Language Association. If that's what you like, go for it. If you happen to be in an area and you just happen to read some things and you like their format better, for instance, I am a member of a couple of professional organizations, and every one of them has a different format. Any one of them is good. A lot of science organizations like APA format, American Psychological Association, they have a really neat format. So all the other sciences say, oh, that's fine. We don't want to make up our own. This is a really good format. Use any one that you want. The main thing is to be consistent. Okay? Now, yeah, there it is. MLA. Okay. Here is a common, not super common, but I've seen it more than once, error. You may be writing along and make a reference to something. And say you made a reference here, and you open parentheses and you put the author's name, comma, year of publication, close it, and go on type. Or whatever your format calls for. And then somewhere down here, you make another reference, and you open parentheses and put the title of the paper, comma, page number. Close it up. Wait a minute. If that's the same kind of a reference, why did you use one format there and another one there? I think I know. Probably this reference here used the format you copied here, and the one that you used down here may have used a different format. Look, you choose the format and do all of them according to that format, okay? That's what I'm talking about, consistency. Now, I know in the various formats, if you're referring to a book, you'll use one thing. If you're referring to a journal article, you'll use it's the same format, but it uses a different presentation. Well, journal articles are different from books, so you'll refer to them differently. Okay. Here's another thing. If you start indenting paragraphs, indent all your paragraphs. I chose to block my paragraphs, so I blocked them all. But I've had papers that started off indenting, then went to blocking, and then maybe went back to indenting, or indented this one to here and this paragraph to here. You're not being consistent. You're going to lose points that way. Okay? I've also had papers do this. They start in Arial, and somewhere in the middle of this paragraph, it suddenly goes to Times New Roman. If you paid any attention at all, you'd see you changed fonts in there. Why? There's no reason to. So it leads me to think you're not really too serious about the paper, so you'll lose some points. So be consistent. Be careful with your paper. Spelling, grammar, sentence structure, all those things they mark off in English class. Yeah, I know most of those things too, even though I'm not an English teacher. So they'll cost you points. So please, every one of your word processing packages, I think today, has spell check. And I can guarantee you there are probably 2 or 3 papers that were turned in the first mini-term that I swear they did not use spell check. That did not use grammar check, or I wouldn't have seen the errors I saw in those papers. They just and waited till the end of the term, typed it out, and turned it in. They didn't even proof it, I bet. But I know they didn't use spell check or grammar check, or it would have caught half of that. Okay? Use good proofreading. I had an English teacher in high school that used this phrase. She said, when you do a major paper like this, get it done ahead of time. And then here's what she said. Let it rest. Set it down. Let it rest over a weekend. Don't look at it again for a few days. Pick it up, and the phrase she used, with fresh eyes. Read it. And if you say, what was I saying? Then probably I will be saying, what is he saying? Okay, so read it with fresh eyes. That's what I mean by good proofreading. Let it sit for a few days. Pick it up. Even have your sister, your brother, your girlfriend, your boyfriend, whoever, look at it. I wrote a letter not long ago I intended to send to the editor of the paper. Made the mistake of letting my wife read. Nah, I don't understand that. You do this. She's a very good editor. So before I ever send it, it's going to go through her, right? So use good proofreading. Does that mean have your girlfriend write it for you? No, I didn't say that. Okay, so don't even try that either. Okay. Now, Content also matters. I've been talking about English stuff, but content matters. Literally, and we'll talk about Isaac Newton a lot. I probably read more papers on Isaac Newton than I ever thought I'd read in my lifetime. And there have been good papers generally. I remember one, I'm just making up the dates now, so I don't remember stuff. They had in parentheses, after they mentioned his name the first time, you don't have to do this, but they chose to do it, in parentheses, the year of his birth, comma, the year of his death, and then they went on writing. And then over on page 2, they had that he died a different year than he did on page 1. They said the paper wasn't that long. I mean, it couldn't have been that much difference there. It was just sloppiness. Or I've also had this. Let's say someone referred to something that happened in 1492, not when Columbus sailed the ocean blue, not that, but they typed 1942. Guess what? I could tell that was an error because I knew that didn't happen in 1942. It happened in 1492. So be careful. Content also matters. In math classes, I've had a lot of papers on Pythagorean theorem, and believe it or not, I've had some that stated the theorem wrong, okay? Just got it completely wrong, and I could tell that, so content matters. So be careful, okay? When is it due? The paper is due by the last day of class before the final examination, okay? Since this is a mini-term, the last day that you're in the room will be your final exam day. The day before that, you don't have a whole week. Everybody else will have the whole week of finals. We have class the first day on Tuesday and the final on Thursday, okay? So the paper is due by that last day of class. I've just made up. If that was Tuesday before a final exam on Thursday, or vice versa, if the final exam's on Tuesday, then the paper's due on Thursday before that, okay? But I highly recommend start working on it now. That's why I want you to give me the title as soon as you can so you start thinking about it. Because guess what? You'll never have more time to work on the paper than you do right now. You said you're in an English class, right? Okay, I bet you toward the end of the term you're going to have papers and projects and rewrites out of the ears. You may already be having that now because it's in the middle of the term. Those are your only mini-term courses. Probably don't have many assignments yet, right? But I bet you at the end of the term you're going to have tons of them. Presentations, PowerPoints, or other things. So try to get started as soon as possible. Okay? You will lose points if the paper is submitted after the last day of class. So get it to me. Don't put it off till then. Now here's another thing. I've been teaching, like I said, either my 19th or 20th year. And probably the first 5 years or so, maybe less than that, fewer than that, I didn't assign papers. But I started being sent to meetings, SACs, accreditation meetings, those kinds of things, and they were really pushing writing across the curriculum. And that's when I decided, yeah, I really need to start doing that because this is the kind of stuff they're going to look at. So I decided to start doing it. So every math class, every physics class, every physical science class I've taught since I started that has had papers. And this is about an average size class. This is 15 students are supposed to be in here. I'd say my average class size is between 15 and 20. Now I've had some classes with 32 and 35, may have had 1 or 2 with 40 or more. But I've also had small classes too, okay? But I've also had classes this term. This is my 8th class this term. Now most instructors don't have that many, but I have a lot of small classes where classes that students need to graduate. So I have 4 people in differential equation 4 and Cal 3, that kind of stuff. So I have a lot of small classes, but every one of them, every student has written a paper. This is for 15 years approximately. And I've taught every term. Fall, winter, spring, fall, spring, summer, since we've been on semesters. Back when we were on quarters, fall, winter, spring, and summer, all of them had, after the first 5 years or so, had papers. So it's been a lot of papers. Multiply all those things, yeah, a lot of papers. And this is a gross generalization, but usually the papers that come in earliest in the term, usually, not always, are some of my best papers. And quite often the ones that come in that last day are some of the worst papers because, like I said, they're typing them up, turning them in without even proofing, without doing anything. Now, I've had some real dogs at the beginning. I've had some great papers at the end, but the general trend is basically downhill. So get started early, take plenty of time, do your research, do what you can. Okay? Now, that's all the stick. Here's the carrot. If you submit your paper, these are the days, the things I've got to change. Okay, this is March. If you submit your paper this month, the month of March, this is what I got to change because this was the one I used back in fall term. That was October. But if you turn it in the month of March, you'll get 2 bonus points. If you turn it in the month of April, you'll get 1 bonus point. If you turn it in the month of May, you get your score. If you turn it in after the last day of class, which will probably be in the month of May, so you only have 1 day there probably that you'll get 0 points, you start losing points for being late. Now, here's one more thing that I require that most other instructors don't. When you submit your paper, please attach a single page from one of your sources. Now, you might have 3 sources. Pick a page from one source. I don't need one from all 3. And I don't need the whole source. Now, if it's a book or a magazine or journal out of the library, take it over to the copy machine, copy me a single page from that book, journal, magazine, whatever. If it's something you get off the internet, then print me a single page. I don't need the whole article. A single page and attach it with your paper. Okay? If you don't have that, you're going to lose points there. Now, what if you do that thing, like I said, the internet application? If it's a YouTube video, how are you going to print a page from that? You probably can't. If you can, fine, do it. But if you can't, just give me the link. Okay? I will check the link. If it's bogus, you're going to get bogus points. And bogus points are big points, by the way. Okay? So, take it off. Okay? So, just for that, all you can do is send it to them. Okay? For that page. Okay. Any other questions? Or any questions on the research? Second? Yes, of course. Whatever format you use, your format is going to tell you how to use your citations, works cited, references, whatever your format calls for, that's what you do. Yeah. So, yeah, you'll need to do that, however your format calls for it. That's why I don't put it up here, because if you use a different format, it may call it something different. But, yeah, you do report what you use. Absolutely. Okay? Good question. Thank you. Any others? All right. If that's the case, then I'll go on and close this off. When I make these 2 corrections there, October becomes March and November becomes April. Once I make those 2 corrections, this will be out on Blackboard. Okay? Now, you weren't in the room when I showed you how to access the thing on Blackboard, were you? Okay. I'll do that in just a minute. All right. Let me close this out. And now, I have the locator card for first mini-term done. I don't have it done for second, but I'll show you what it's going to be. Here is spring 17 first mini-term. Okay? This shows when I'm in class, when I'm not. I'm here typically every day right around 7:45. Try to be here a little early. Sometimes traffic doesn't agree and stuff. But I've got 8 o'clock classes across the board except Friday, but I still try to be there by 7:45. Okay? And most of the time I am. We have classes 8 o'clock every day, 9:30 every day. Mondays and Wednesdays, there's the longer classes, and Tuesday, Thursday, they're regular length classes. Then my lunch varies depending on what day it is. On Monday, Wednesday, I have afternoon classes. This was Physical Science 111, which I had last term with Brittany and Terry. Yes.
I had a question on, I'm not sure if our instructor is going to do anything, but on certain days we're short on our lunch.
On certain days, what?
Like on Tuesdays and Thursdays.
Okay. And what about? I couldn't hear what you said.
I was wondering if some days I could come in like 15 minutes later. sometimes traffic doesn't agree with us on the way back.
Right. Oh, okay. Okay. I'll put it this way. Technically, and this is just what I was going to say, our class doesn't start at 12:30 like first one term because y'all have, yeah. I understand you get out at 1 typically, and I'll have 15 minutes for lunch. Well, I wish they'd have told me that ahead of time. I asked him what time they wanted me to start, and he said, oh, 1:15 is fine, because I assumed you ate before your previous class, but you don't. Okay, you eat after. So, yeah. Second?
I said, because we're in there from 8 till we come here.
Oh, you do? No break.
We're all the way through.
Okay.
I'm in the term before this class. It's supposed to get out at 1:30. This class started at 1:15, so that was a little overlap. My instructor this morning said he would try to work with me, but
Right.
some
Okay.
days we're going to be testing at the end of class.
Right. And I understand that. And here's how I'm going to answer that. Because we don't start until 1:15, like I said, if I'd have known, I could have started later. But that puts us down to 5:45, okay? In fact, it's off the scale here, so let me get on down here. So I will do this on Tuesday and Thursday, then this is going to be 1:15, this will be 3:45, this will move down to here, and that puts me off campus at 6, but I finish teaching at 5:15. At 5:45. Now, if I had known, I could have moved it down because in the first fall term, the automotive students, some of the programs, GM and Toyota, I think, or at least GM, they wanted it in the fall, but they didn't get out until 3 o'clock. Okay, like y'all, I bet y'all were over there until 3, weren't you? They were too. Then we had the physical science class. Well, I was told to start it at 3:15, so we did, and that put us here until 7:45, which is fine. I could have handled that, and I handled it then, I could handle it now, but what I've done, because I was told to do it this time, and that's going to have me getting off campus at 6, I worked my whole first mini-term longer hours, so I wouldn't have to work as long this mini-term. So it's going to be a little tight to change at this late date. But here's what I was going to say. Because I record every class, I'll start at 1:15, which is when I was told to. So if you come in late, you can always go back and listen to it on YouTube and catch anything you missed at the beginning. Okay? And then, like, you have to leave early. Well, see, you'd be missing any more, but, and you sure it starts at 5 on Tuesday, Thursday. Is that Mr. Huh? Yeah, Mr. Brazil. Okay, he's really good too, and he'll work with you some too. He's very nice guy. Yeah. So we can work it out. But again, I teach from 1:15 till 5:45. Okay, that's what's required. And if I'd have known sooner, I could have moved it down, and then I'd have adjusted my hours in the first mini-term. I've already spent those hours, so it's going to be hard to get those back. So, but in the future, I'll find out. When do you think you would like to have had the class started?
I'd like to have it started at about 11 o'clock.
No, you have automotive classes 11, okay? With you getting out of there at 1, what time would you have wanted it to start?
On our schedule, it shows mine at 1:30.
Say again?
It shows this class starting at 1:30.
Oh, really? Okay.
Because that's why our instructor is saying that we're going to have a 30-minute lunch on these days. Because we get out at 1, we're able to go get the food and come back.
I printed this out today, and it says 1:15 to 3:45 to 5:45. Yeah. So, but if you want it in the future, not you, the next group, I can do it at 1:30. No. I want to do what's best for the automotive students.
No, I say we just keep time we got. I'm just trying to figure it out later on Thursday night.
Okay. Well, that's what I was thinking. That's why I asked, and I was told 1:15. Okay. It's gonna be till.
Because I got 2 hours drive to the house.
Yeah.
For Thursday night class.
Yeah. Where you live?
Columbus, Mississippi.
Oh, that's right. You're the one from Mississippi. Okay. Yeah. Say again? Huh? Wow. Well, unfortunately, the class goes till 5:45. Now, not every day it will. That's why I put the labs at the end, unless we have a test, and the test is at the end, the labs right before that. So if you finish the labs early, unless we have a test that day, when you finish the lab, you leave. If we have a test, have the lab before the test, and then the test. If you finish the lab early, you can start the test early. Then if you finish the test early, you can leave then. So I always try to do that Tuesday and Thursday to give you maximum time. I don't want to be lecturing until 5:45. Now today I may be because it's really late, but most days we'll have either labs or tests or both, on most Tuesdays and Thursdays.
Where's the lab gonna be at?
Most of the time we're going to try to use the lab right next to us here at 253. It's a biology lab, but it has nice surfaces and stuff. That's usually a time when there's no biology labs in there, and as long as there's not, we'll use that one. If they're there, we'll try across the hall at 252. If they're there, then we'll try 259. I'll find a place. 250 is a possibility. I'll find a place. I think most of the time it will be 253. I don't know for sure, but I have to work around the biology classes. But again, the 3:45 to 5:45 is not a likely time for them to be in biology lab most days, but I can't swear they won't. Okay. So I'll have to change this. The physical science 111 becomes 112, and it moves down to 11:15 to 3:45, then 3:45 to 5:45, and then this will be 5:45 then, and I'll be off campus at 6. Okay? So, like I say, in the fall it was off campus at 8, which is fine. I can handle it, but I had time to adjust that first mini-term, second mini-term. I don't have much time to adjust it now. Okay. So, that's my locator card. And again, I'll make those corrections. I'll put it out on Blackboard. Now, while we're here, I'm doing this, let me pull up Blackboard because y'all weren't here to see it. Wait, I didn't need to do that, but I've already done it. Let me see if I can do this. It might be faster. Won't move. There we go. Let me pull it up here. Okay, what's it doing? I think I've loaded too many things here. Yuck. It's awfully slow. Okay, I'll end that. Okay. Blackboard. Let's see if this is Blackboard. Still waiting for it. I heard that Blackboard was awfully slow this morning. Have y'all had any trouble on it? What's that? Okay, that may be it. I wondered when the kid told me this morning, or the guy told me this morning, if it might not be our node here was really slow. But he was having trouble even getting on it. Okay. I don't have this one done, but I do have last fall's done. This will be the one for this term, spring 2016. I'll show you the one for fall 16-17. Okay? And now this is the instructor side, but hopefully your side doesn't look a lot different. If you pull up Blackboard, the home page, when you see over here these things under content, that's where you go. Click on content. Okay? Now this was last fall, not this term. Okay? Here you see the syllabus. Now I don't have it out here yet because I've got one minor change to make to it. Research paper instructions, you saw that? 2 minor changes. Locator card, 2 minor changes. Here will be your 2 videos. They're not there yet, but here's what they look like when they are there. You go and click on this, and when you click on this, you'll see a bunch of, I thought you would. You're right. Sometimes it's the thing and sometimes, okay. This is from last term. Here was the first chapters, the second chapter, okay. I don't know why. There's a syllabus one, but it's not showing up here, but I don't know why. Maybe it was in on that. But you see they'll be named or numbered something like this. And you can click on that and you get the whole shebang. Those are the YouTube videos. Okay, yeah, and that's the thing. The old program I used to use was called Integrity, and there you see like a PowerPoint. You see a different screen for everything time I change. You could just click on the one you wanted to see. This one you sort of have to guess on the timeline down there at the bottom. You click here and then it'll go to that place. So you don't have to sit through and listen to it all. But you have to do some guessing on where it might be. So that's the disadvantage. They went from Integrity, which was a great, easy to use package, loaded straight in the Blackboard. I didn't have to sit around and wait it to load on the YouTube and then change it to a playlist. Yeah, I didn't have to do all that. It went straight to Blackboard, and you could access it there. This one, they went cheap. School did, and so yeah, but they don't use YouTube either. But never mind. Okay, but anyway, that's where you go to find that. Okay. Now, they're not there yet, but I'll have it there. Then it may not be in this order. In fact, I usually put the PowerPoints before I put YouTube videos, so it may not be in this order. But there I'll put every chapter PowerPoint so you can access it before class if you want to. So it'll be here under content. But then when you get to YouTube, you'll see the PowerPoints again, but then you'll hear me talk about them. You'll see me write on them because this has a ionizing pen and I can write on it as well, okay? So I did want to show you how to access those, and that's how you do it. Was there any questions on that? I should have asked a question before I closed it. But. Okay. One last thing we have to do before we start on physical science, and that's this, safety. Now, it's not nearly as involved as safety you have in your shop, okay? That's pretty important stuff. But we still need to talk about 3 items of safety, even over here on the classroom side. Any idea what they might be? Say again? Okay, no, we don't need anything with safety glasses. Nothing you'll be doing in the lab will require those. But it's that's all shop type stuff, okay? How about here? What do we have going outside? It's just a shower today. If we had severe thunderstorms, and this, folks, is the time of year for it. March, April, May. What happened April? Yeah, we could have any weather issue. Hopefully we won't. But what was it, April 11th? About 3 or 4 years ago? The major tornado set was 27th. I mean, unbelievable the number of tornadoes in Alabama that day. What do we do if we hear that weather alarm go off? Say again? Yeah, at least. Yeah, north to south, everybody was getting whammed with it. Tuscaloosa especially badly. Phil Campbell got smashed. Another town somewhere up there, Pleasant Grove got hit awfully hard. I mean, all over the place. It was incredible. What do we do if we hear that siren go off? Say again?
Run.
No, we walk and go slowly. Okay, here we are up here on the second floor in this corner office, right? For the classroom. What we do is come out of the building, out of the room, take a left, go down this half flight of stairs, take an immediate left there, go down one more flight of stairs, complete flight. You want to go as low and as interior as possible. And that's as low as an interior as you can go. When you go down on the first floor, which looks a lot like this, one of the safest places to be, though maybe not the most pleasant places to be, would be the restrooms. Because there the walls are pretty close together, and where you have your greatest strength is where you have the greatest walls, especially the corners. Corners are stronger than open walls, okay? Because you got 2, degrees of non-freedom here. You have a great strength in a corner. So the restrooms are pretty good. two sort of negative things about restrooms. Number one, maybe not the most pleasant place to pee, for an hour or two. But number two, if we really do have a serious weather problem, the odds are we're going to lose power. So then you'd be in the dark in the restroom, which is not the best place. Huh? So the next best, okay, right next to the restroom, down on the first floor, okay, lowest level, interior. Don't go to the exterior. Wherever there's windows, there's danger of flying glass. With a tornado or heavy, strong winds of any nature, things can come flying in the window. You can get cut. Don't go interior. Next door to the restroom is a little office, and it's the academic dean's office. Now, most of the time, she's not here. Most of the time, the associate dean is not here. There is another guy who uses it, so most of the time, he's not here. But if they are here and the room's open and they invite you in, not a bad place to be, again, because the walls are relatively close together with several corners. More strength in the corners. So if that's not available, probably the next place would be the hallway. Now the hallway, the walls are relatively close, not as close as those other rooms, relatively close. But the advantage of the hallway is they do have emergency lighting on either end. So you will be able to see if the power goes off. Okay? After the hallway, then, there's a classroom here. This is underneath 256. It's room 160. It's where your math class is going to be, I bet. Okay? That's not a bad place to be either. It's open space like this, so don't be in the middle. But as long as you're close to a wall, especially a corner, that's not a bad place to be. Okay? Next to that, you have to go through in the hall here, the glass doors into the library. But right there, underneath these offices, is a computer room. Now that's a little bit smaller than the classroom, so the walls are closer and the corners, are closer. But neither one of these have emergency lighting either. Next to that is a room I call the reference room in the library. That's where the atlases are, the big books like this that you use for reference. That is not a bad place either. The only trouble there is you have quite a few stacks of books. I guess they could fall, but usually you won't be. They're interior, so it's probably pretty safe. I wouldn't go any further in the library, because any further you're at outside areas. You're exposed to glass. Don't go low and go interior. That's what you remember in weather situations. Now, that's one item. How do we go? We don't run. We walk. We go slowly and carefully. Now, all of you look pretty able-bodied now, but I guess it's possible that some of you might go skiing at spring break and come back with a broken leg. And if that's the case, I'm going to be going down those stairs with you. I'm going to make sure you get to the bottom safely. If I need to help carry you, I'll maybe get one of you other able-bodied people, and we'll help you down the stairs. But I may be the last person down there, because I want to make sure everybody's out of the classroom. When I get down there, I'm going to carry my book and a pen, and I'm going to call the roll, because we have to account for everybody. So when you go down, don't think, hey, I think I can beat the storm home. Famous last words. You do not want to be in a car when there's a tornado there. Say again? I couldn't hear.
Hold my beer.
Okay. Yeah, you don't want to be there. Okay, so don't. So when I go downstairs, I'm going to call roll. When I call roll, if we're missing somebody, that means some emergency responder or me or somebody else will have to come up here looking for you. Okay, and if you're out of the building or went to visit friends or something like that, you're putting somebody else in harm's way, maybe danger of life or limb. Okay, so stay together at least until we get the roll call. Then then if you want to mingle around, you can, but don't leave the building. Stay low and interior. Okay, that's most of what I can think of for weather emergency. What's another emergency we might have? Fire, exactly. Let's just imagine first that suddenly we see smoke coming out of this ventilation right here. We're the first people in the building to realize there's a problem in that mechanical room right next door. You smell it? What do we do? Full fire alarm. Excellent first suggestion. Where is the closest fire alarm to where we are right here? Anyone know? Okay, good guess, but wrong. Why? This part of the building here is the oldest part of the building. It's a big old horseshoe here. Built before fire alarms were required by code. We don't have a fire alarm on any of these hallways here. Any of them.
We get out and everybody.
So where do we go? Okay, and here's what I recommend. I would say go in a pair. Two people go out the door here, take a left, go down this half flight of stairs, go to this corridor over here. This is the one that goes across to financial services here. As soon as you get on that hallway there, that's the newest part of the building. Those halls do have fire alarms. So you find the closest one, when you turn the corner, out the corridor here, look to your left, look to your right, you'll find the fire alarm on this side. Go over there and pull it. Okay. So one or two people have gone to pull the fire alarm. How about somebody else? What's the first thing? We're the first people to know this is a problem. Say again?
They said go jump out the window.
Okay, please don't, because I have to write up all sorts of reports on why you have a broken leg. I don't want to write them up. I mean, you're valuable, but you're not that valuable. Okay. Okay. I knew you were. Okay. Now, what else? Okay. You were here. They did it wrong last time. Okay. A good idea, but even before that, remember we're the first to know. Someone went to do an alarm, somebody else pull out your 911. Now, actually, better than 911, do any of you have campus police on your speed dial?
How's that better than campus police?
Huh?
You're the ad of middleman.
Okay. If you do, that's a good idea to have. Put the campus police on your speed dial. Dial them. They'll get in touch with you. If you don't have them, dial 911. That's the second best choice. Okay? So, somebody's doing that. Somebody's pulling the alarm. And the rest of us, like you said, except when we had the fire drill last fall, that's what you're going by? You weren't here? Okay. You said go out in the parking lot and back. That's not quite right. You go to a parking lot, but you see if there's a bit emergency in the building. In the building, what you do is get out the closest door that's safe. For us, you go out this door, down the half flight of stairs, go down that same flight you did, but don't go interior, go exterior. Okay? You get away from the building as soon as possible. Last fall, they had us do a fire drill, and they told everybody to go to the back of the building. Wrong answer. Okay? I emailed them back and said no. What we're supposed to do is get out the closest. Now, if you want us to go to the back, do that. But don't practice bad behavior. Bad behavior for everybody to go out the same doors, especially going by places that could be burned. You get out of the building as soon as possible. Now, where we would go, this is a picture of the building right here. We are right here in this classroom here. Okay? I'll make sure I'm saying this right. Yeah. No, we're in this room right here. Okay. There's the library down that way. Okay, we're in this room here. We go out of the building, and then we head to the parking lot right down there. Okay? That parking lot right down there. I would say the grassy area would be better than the parking lot, but they say go to the parking lot, so we'll go to the parking lot. Okay. And again, I will go with the last person out, helping them if they need assistance. Hopefully you'll all still be able-bodied. And we get out of the building. You get at least 75 feet from the building. Why do you want to get so far from the building? Would it be safe to be right up against the building?
Explosion.
Yes, you could have an explosion, and then the glass is going to be flying outward, not inward. Okay? So get away from the building. Absolutely right. And they say go to the parking lot, we'll go to the parking lot. Now, last time we had, and they say we're going to have a fire drill again this time, and they told me we'll do it right this time. Well, they did it wrong last time. I said, it's fine to go out, but when I took my class out, when we had the fire drill, we went out this door, not right from the one they told us. I said, now, normally we'd be going there. They want us back here, so we went around this way, because it's just a drill. But I said, don't practice wrong behavior. Practice what you're supposed to do. And that's what you're supposed to do. Again, we stay together because I'm going to carry my roll book. I'm going to call the roll. If we're missing anyone, someone has to come back into a burning building and risk life and limb trying to look for you because you wandered off to join your friend somewhere else. I realize most of you have your friends right here, but sometimes that would happen. You stay together until we call roll, and then when they let us know, hey, it looks like we're going to cancel class today, then you go home. Or they say, no, we're going to redistribute to other buildings. Or no, we're going to blah, blah, whatever. They'll make a decision. So it was really just a small smoke. It's already been taken care of. You can go back to class. They will let us know, don't take off and head home. Otherwise, someone's risking life or limb. Okay? So there's outside problems, weather. Interior problems, fire, chemical spill, something like that. Okay? What's another safety issue?
Earthquake.
Say again?
Earthquake.
Well, earthquake would be just like second, a gunman in the building. They call it nowadays active shooter. Okay? Now, guess what? I'm hard of hearing. So if there is our gunfire, if it does start somewhere in the building, you'll probably hear it before I will. Okay? Okay, so what do we do?
Shoot back.
Okay, no, you're absolutely right. First thing we do, someone get on the phone and dial 911 and tell them we hear gunfire somewhere. Okay? You do that. Okay, here's the problem. Okay? This is the problem in this location. That's why we go over. What I do, this door is lockable, but it does have buttons on the side here for you to just punch it. I have to go outside and lock from the outside. So I will do that. I have a key for it. Then I will come inside. Don't you go pulling the door too. Okay? I will come back in and we'll close the door. It'll be locked from there. However, we have another entrance this way. Okay? Now, okay. We'll get there. The trouble is the door over there. Now, the good news is quite often security forgets to unlock that classroom door, and I don't know why. So if they have forgotten to unlock it, we go over there and close the door, so it's locked too, but then we come back in here, okay? But we do that. But if that one's not locked, if it's unlocked, I don't have a key to lock that. Now, you might say, can we lock this door? Yes, I can. This has buttons right here. But guess what? It locks from the inside, but not from the outside, so this does us no good except locks us into the room. This door has a deadbolt, but I don't have a key to this. However,
We screwed.
however,
So what you mean is just bring it
Hold on,
out.
sugar, we outside.
Okay, go ahead.
Can you give me about 5 minutes to come back?
While I lock this door, if you want to, don't, I'll come lock it. But if you want to, go and lock this door. Now, check that door there. If pushing, check the knob. If it's locked, close that door and lock that door, and then come back in. Close this door too. Why that? Oh, why? You can shoot through the window, bust through the window, and unlock it from the outside. But if this door is closed, you can't see if anyone's in here. And that leads to what we do next. What we do next, because there is a window here, what we do next, if there's active shooting, I've locked this, we secure that as much as possible, we all get right over here.
That's what I said.
He can shoot through the door and still do us damage. He can look through here to see if anyone's in here. We turn off the light, we get as quiet as possible, and we get over here. He can't shoot through concrete block walls. Not very well, okay? We'll get him right against the wall in case it does go through. No, I'm just kidding, okay? All right. So, we get over there and we're as quiet as possible, okay? Until we hear officially it's okay. I hate like everything, we even have to mention this. But I only know of one, but there has been one, at least one community college shooting in the country. That was several years ago. Hopefully it's not going to happen again, but there's no guarantee. Several universities have had shootings, and several nightclubs and movie houses and other things.
Nobody really cares about us.
What's that?
No one really cares about us. We ain't important about it.
Yeah. Well, believe it or not, after 9/11, were y'all born then?
Yeah.
Okay, good. Okay. I'm just kidding. Okay, I was too. I was here teaching, and they started inspecting mail because about the same time anthrax and other things. That's when they really started doing things, and had us do what we do in case. I thought, yeah, New York was hit, Washington was hit, Bessemer was next on the list. I know. It happened. No, I'm just kidding. Okay. Yeah, right. Okay. But everybody panicked. So, but we always, good old Boy Scout, be prepared. So be able to think through what you do. If that emergency, this emergency, that emergency, whatever, think about what you need to do. Okay. I think we've hit all of the exterior things we need to do. Let's go to real physical science now. Okay. And as I mentioned, we start in Chapter 1. And Chapter 1 is one of these nebulous little chapters that they have at the beginning of a lot of science books. What is science? Or some silly question like that. But really, there is some value in it, especially in that few things we are going to cover in this chapter, they'll cover in later chapters without going back over them. So I decided, yeah, we probably do need to hit this. Here's the core concept. And if you have a book, I know most of you don't yet, but if you have a book, the core concepts are given. They put white print on yellow background, which is really hard to read. This is a lot easier to read. Science is a way of thinking about and understanding your environment. Now, when they mean your environment, they don't mean the trees and things like that, though it's certainly that, but just the stuff around you. Your environment may be a car, the body of a car. It may be a shop. It may be a classroom. It may be your home. It's understanding how to think about and understand what's going on around you. That's what science is trying to do. So what is science? And here's a few quotes. And most of these I think are a little weak. But search for sense. Yeah, you can think of it in that way. In other words, understanding what makes things happen. Finding order of your surroundings. Again, that's understanding your environment. Some people think of science as tools and rules. That's pretty narrow, but it certainly does have tools and certain rules to follow. I don't know why this picture here, it's a pretty picture, but can anyone see any science going on here?
Trees growing.
Trees are growing, and it's obviously a pleasant time of year. They've leafed out. It's probably late spring, early summer at least. People are in shorts, okay? So, say again? Okay, the architecture of the building. Science was behind most of that, okay? That's why the buildings are still standing. That's why they have the columns. There's all the supports there, okay? Even the bell tower or whatever that happens to be there. Okay, science is involved in motion. All these people are moving. They're burning calories. That's chemistry. That's physics. That's biology. The strapping things to the back. This is the correct way to be wearing a backpack. Have it slung over it. Well, that's not too bad, but I always carry it just over one shoulder. Not good physiologically. That's the better way to do it there. Most people do it. But this guy, he has it slung over just one shoulder. Probably going to have some shoulder problems if he carries too heavy of loads that way. So yeah, there's physics, there's science going on all over the picture, whether you realize it or not. Okay? So, what is this chapter going to be about? It's basically split into two pieces. The first half, or a little over half, quantitative descriptions, and then a little on the nature of science and how we do things. So, I'm not going to go over these, but we're going to talk about objects and properties, quantifying properties, okay? Talk about them here. How do we measure them here? Measurement systems, okay? We'll talk about a couple of possibilities, especially the metric units. I bet you all using that in automotive construction these days. The older vehicles, U.S. customary, 3/4, 5/8, 7/16, not anymore, 11, 12, whatever millimeter, right? Okay, metric units. Even though we do everything else in English, U.S. customary units, a lot of things that are done internationally, like selling cars, you have to have metric. We'll look at the metric prefixes. That's how we understand these things. And we'll see what kind of understanding we get from our measurements. Okay? this is sort of a big section here. It's understated here. When we get to it, we'll spend a little more time. Then we'll look at some of this nebulous stuff. Well, not just nebulous. Scientific method, it's going to use it throughout the rest of the chapters. Explanations and investigations, laws and principles. This will just be for getting terminology, models, and theories. We'll talk about a few things. You might think of some paper topics when we do some of those. Most of what we're going to do is in this part and the first little part of that. Okay? Now, let's start with objects and properties. Objects are obviously things that can be seen, touched, measured, linked, whatever. Objects, things that can be seen or touched. The properties are then the quantities or qualities attributed to that object. This device here has a length, it has a width, it has a thickness, it has color, it has buttons, it has connections, it has an antenna type place here or here, somewhere there, that's sending signals to here. Those are the properties of that object. Color, shape, size, weight, mass, how fast I throw it, no, okay, okay. So, those are properties of the object. Now, I don't think I ever see or use this term anywhere but in this chapter, in this book, reference. Okay? It's a legitimate word, but it's a comparative property in other more familiar objects. Really a nebulous kind of concept here. Like you say, oh, sky blue. And that was the other thing I was going to say about this picture back here. Notice, not a cloud in the sky. Pretty likely not to rain that day. That's not like today here, is it? Okay? That makes me think this is somewhere out west. It doesn't have to be, but most of the places down here, you almost always have a few clouds somewhere. Didn't see any there. Okay. But sky blue, when I saw that, I thought of that. Lemon yellow. That's pretty weak. Okay? I think what they really mean by reference, okay, and we'll talk about this a little later. If I ask you, okay, here's a desk, that's an object. One of the properties of the desk would be the length of the top. How could you measure the length of the top of that desk? Well, you might take your fingers and go, well, there's 1 span, 2 spans, 3 spans, 4 spans. And if you knew how big your span was, you have a decent estimate of the size of the desk, right? That's not very precise, but that would be your reference. Reference, okay? How long it is from thumb to finger. And a lot of people are really good at doing that kind of stuff and estimating that well. Someone else might take, well, here I have a measure. It's 1 cap, 2 caps, 3 caps, 4 caps. That'd be a lot of time to count how many caps it is across there. Or lengths of markers, 1 marker, 2 marker, 3. Those would be your reference. Not really good reference to use, any more than sky blue or lemon yellow, okay? Those are not very good reference either. So what we want to do is find reference that are common, well-defined, and usable, okay? And you can have some really good ones and some that aren't so good. The problem, well, I've just been describing, language can be subjective. Sky blue in Montana may be a little different from sky blue in Florida, okay? Because in Florida, you almost always have clouds. Montana, big sky country, okay? So, yeah, it can be subjective. It can be ambiguous and sometimes even circular. Well, sort of like something, and you go back and around and you're saying the same thing you're trying to describe. So it's not very good. So we need things a little more precise than that. So we use quantifying properties. So in measurement, we use the quantifying reference, and these are what we call units. Now, the units could be caps, markers, spans, or whatever. Those are not really great units, but they could be, okay, could be used. But you compare the reference unit to the property being described, okay? Now, what's a common length unit? Name one. Foot, is that what you said? Okay, yeah, you could use a foot. Now, you mean a real foot, or you mean a 12-inch foot? Yeah, if I had a measuring stick, which we'll have in the lab. Don't think we're going to get there today, but you could take that measuring stick and measure. Yeah, foot would be a good unit to use because this desk is so many feet long. Okay? What's another common reference besides foot? Meter. You could use a meter stick. By the way, a meter stick, this is just an approximation, is about, okay, a yard is about the distance from your nose to the tip of the finger. Not exact, because everybody has different safety length long. That's a pretty good guess. A meter is the opposite ear to the tip of the finger. That's just a little bit further than a yard. Okay? So if you had a meter stick, this would be probably 1 meter stick here and a few centimeters left over. Okay? That would be a decent reference. What would be another unit you could use to measure length? Yard, we already said, basically, yeah, you use a yardstick, not a meter stick. Be just a little bit more yards. Second, millimeter. Yeah, we could do millimeters. Now, here's about what a millimeter is. A millimeter is about the thickness of a dime. So we could say, we could do it. Probably not the best one, right? Okay? But we could use it. What's another unit for length? A mile, yeah. How many miles is this desk? 0.000. Okay.
So
Be a
very shy of a mile.
Yeah, a little shy of a mile. Yeah, exactly. Okay. So you see some reference units make sense for the desk. Inches, feet, meters, yards. Centimeters wouldn't even be bad. But some make no sense because they're too short. Like, I think inches would be too short, or pretty short for that. Millimeters certainly would be bad. Miles would be too long. Okay? So you compare the reference unit to the property being described and pick one that makes sense. Follow a procedure specifying how the comparison is to be done. So if I'm using a span here, and I do that, then I'll put this finger here. That's 2 span, 3 span, yeah, something like that. You have to describe how you're going to do it. If it's a foot ruler, then put it here, make a little mark, put it here. Yeah, you just describe how you're going to do it. Follow a procedure specifying how the comparison is being done. Count the number of standard units to describe the property under this thing. 57 caps, 12 or 13 of those, whatever, okay? Counting how many you use. Now, here's the big deal, folks. When you're making measurements, you're always going to come up with a number. You counted how many of those reference units, right? But do you just put the number down? No, you always have to put the name. Caps, millimeters, centimeters, miles, inches, yards. You put the name with the number because the number by itself tells you almost nothing. In fact, I've heard this and I've actually read it. I can't remember the details, but one of the early, a little bit of background. In the 1960s, it was shortly after World War II was over, quite a few years, but several, and there were 2 big superpowers left on the planet. Soviet Union, U.S. Europe was pretty powerful too, but we were aligned with NATO and stuff with them. But really the big 2 were U.S. and Soviet Union. And the Germans during World War II had really jumped ahead of everybody with their missiles. Remember, they fired those missiles, what do they call V-12s or something like that, from Germany and just plastered Britain really badly. Okay? They also did a lot of bombing of Britain. Britain, they suffered big time because they were within range of Germans' missiles, and nobody had missiles that could fire back at those ranges. So, really bizarre, at the end of World War II, the biggest thing was not establishing peace, not establishing the end of hostilities or anything else. The biggest thing was who could get most of the German scientists, The Russians went after all they could, and the U.S. and Europe went after all they could. Who cared about stuff? They wanted those scientists. They wanted those rocket specialists. Any names come to mind when I say a German rocket? Second? Albert Einstein, he had actually left beforehand because he was Jewish. Wasn't good for him to stay there. So yeah, we got him before the war.
Yeah, I bet you government felt pretty stupid about that one.
What's that?
So I bet you they felt pretty stupid about that one.
They should have, but they were pretty arrogant. I don't think they felt stupid about much, but they should have.
In the space program.
Okay, yes. Can anyone name any of the names? Have you ever heard of Oppenheimer? Werner von Braun? Anyone from Huntsville? Von Braun Center? He was at Huntsville in the space program there. Okay? Bunches of the people were in Huntsville. Wherever there was rocketry going on, Russia got their handful of them too, and we got into the space race. Cold War was going on, sure, but really the space race was big. And Russia started beating our pants off, okay? Because we weren't really that focused. We're trying to rebuild Europe and doing that kind of, they were sending, developing rockets and stuff. So we got a little bit behind them. Remember the first one they got up? Sputnik, exactly, okay? And then they got the first man up. I don't remember his name. And by the way, I mentioned Hidden Figures. This was that time. We were in the space race, and Russia was beating us. So we started calling in and recruiting great mathematicians and scientists to come help us do the calculations, figure out how we could get big rockets out of the Earth's gravitational field through this thick, messy atmosphere and get up there and get out there. Okay? That's what Hidden Figures, part of what it's about. Okay? So, anyway, what the U.S. did was start pouring money into NASA, National Aeronautic and Space Administration, NASA, Huntsville, Houston, somewhere in California, Jet Propulsion Lab, Pasadena, wherever that was. Lots of places. Langley was one big place. That's where the movie was, Langley, Virginia. Okay? So we started pouring money into that. And for probably a decade, 2 decades or so, if NASA wanted it, NASA got it, because we were racing with the Russians. John F. Kennedy came out and said, before the decade is over, we'll put a man on the moon. Just barely made it, but we did it, okay? We beat them to the moon. They beat us into space. They beat us with man into space, but we got to the moon first. I'm sure they have by now. But they started sending things other places because they didn't want to get shown up so badly. That we had already been there, so they acted like it wasn't important. So, politics. Yeah. And right now we're using the Russian Soyuz space. No, we're using the International Space Station, but we're using Russian rockets mostly to get the supplies back and forth because we retired our. Yeah, and that's it. Along about came the time when they said, look, we can't keep spending all this money, pouring all this money into NASA. We need to start cutting back. So they said, look, we don't have to pay all these high-paid NASA scientists to do all this work for us. We've got these universities, we've got these national laboratories, they're out there, let's use them. So rather than having NASA develop the packages, they said, let's put them up for bid. Okay? And so they did. They had this one, and I think the first program, after Congress decided to cut back NASA's funding and make it extramural, not intramural funding, they said, okay, you have them bid on this. You don't have to do the work, get the labs to do it, get the universities to do it. So they tried it, and it was a Martian thing. We were going to send a probe to Mars and, take pictures, take measurements, and stuff like this. One of the Mariner programs, I don't know which one. So anyway, NASA did. They put out the proposals, different entities bid on different pieces they thought they could do. They came up with good ideas. They could come up cheaper than NASA could do it on their own. They had more manpower, more things, and NASA didn't have to do it all. So, and it looked like it was going to get done faster and cheaper. Okay, the politicians liked it. So, one team, I'm just making up part of this, did the calculations to get the spacecraft launched and out of the atmosphere. And then another part did on getting it out of the atmosphere, or from getting out of the atmosphere to orbiting around the Earth. And then another one did how to get the orbits to sling us into space, to time it so we came when Mars happened to be fairly close to us. Okay? And then another team bid on how to come out of that projectile motion into circling Mars. And then another to how to take it back. So they split it up. Now, those may not have been the steps, but that's approximate. So every group bid on it, every group, and it looked like it was going well. Plans were made, they launched it, perfect launch. Okay? Went into orbit, came out of the launch into the orbit, perfect transition. Circled the globes right, took off, got the right propulsion, headed toward Mars. Perfect. Everything was going, different groups had done different parts. And then it got close to Mars and went to go into the orbit around Mars. It turned and crashed directly into Mars. It got maybe 5-10 minutes worth of data on this way down. What went wrong? The team that sent it from Earth to Mars, they had been using one set of units, and the team that took the data from them and were going to start orbiting Mars, someone had knocked off the unit. That team assumed they were using a different set of units. One was using U.S. customary, one was using metric. They didn't put the units down. They assumed it was the other. It was the wrong one. And therefore, when they made the turn, it was too sharp a turn and crashed right into the planet. About a $6 billion mistake. I'm just making up a number, something like that. Now, I hope that you get rich and famous and good enough that you can one day make a $6 billion mistake. I don't think I'll ever get there, okay? But, yeah, he probably wasn't working there much longer. Whoever was that responsibility. Why? Because he read a number or wrote down a number but forgot to put the reference unit in. And the other guy, rather than asking, he assumed. And in the Navy, they used to have a saying about assuming. I don't know if you ever... Huh? Yeah, you got it. Okay. Y'all were in the Navy, were you? Okay. All right. So let's look at some of these measurement systems. And these are based on some sort of standardized units. The English system, which was very good, used for many years. In fact, England being the queen of the ocean, had colonies, the sun never set on the Union Jack, all that kind of stuff. Had people all around the world. Many of those units were based on body parts. Like I said, this was a yard, that was a foot, that was an inch, and they're pretty close to being right, too. But different people have different thumb joints, But that was what they were based on. One was not body parts, but barley corns. One person said, let's make an inch, 3 barley corns laid end to end to end, okay? In a good year, that may be big. Yeah, okay. Not the best of ways to do it, okay? One of the worst things was it, how are they related to each other? How many inches in a foot? 12. How many feet in a yard? 3. How many yards in a mile? 1,760. Oh, what a nice round number. Where do these numbers come from? Well, they came because they were developed in different ways. Okay? So say again?
They just laid out north and he said, well, that's about enough for a mile.
Yeah.
About enough for now. We'll call this a mile.
Actually, the only way I remember that is back when I was in high school, when we ran track, we ran English units. We didn't run metric units. And there were several races. The 100-yard dash, which is now the 100-meter dash, which is a little bit longer. Then there was the 220, which was half a lap around the football field. It was 220 yards. Now it's 200 meters, which is a little bit shorter, but not that much shorter. And then there's 440, which is 1 lap around the football field, which is now the 400 meters. And then that 1 lap was 440, and 4 laps made a mile. So 4 times 440 is 1760. That's outdoor track, yeah. We didn't have any place to run indoors, so yeah, we ran outdoor track. I went to a poor rural high school in Georgia, so yeah, that's how I remember that. And then how many feet in a mile? 5,280. Multiply the 1760 by 3 and you get that. What weird numbers, okay? How about let's go into weight. How many ounces in a pound? Not 12, no 12 inches in a foot, but 16 ounces in a pound, that's right. How many pounds in a ton? 2,000. Well, that's a nice round number, but where does that have to do with 16? There's not really any connection, okay? Well, let's go to liquid measures. They use ounces too, but those are fluid ounces. How many fluid ounces in a teaspoon? I don't know. And then how many ounces in a cup, and cups in a pint, and pints in a quart, and quarts in a gallon? Sometimes it's 2, sometimes it's 4, sometimes it goes crazy. Okay? So here's the problem. The different units are not systematically related. So, man, you have to remember all these weird conversions. Now, if you use them often enough, yeah, we know them. We're used to miles and inches and feet and yards and stuff. But in the metric system, which really the title today they use is SI. Does anyone know what SI stands for? Okay. Say again? No, it's System International. In other words, International System. Now, why do they say System International? Because it's French. They say Système International. French quite often put the noun first and the adjective afterwards, whereas we put international system, they say System International. Okay? Now notice here, English, French. If the English said jump, the French said get down. I mean, they always did the opposite thing. They were always at war. One time they fought a 100-year war. They were just always disagreeing with each other. They were the biggest rivals on the planet for centuries, okay? Well, the English had a pretty good system because England was a little set of islands over here. And they were pretty small, and everybody pretty much agreed. France was not a huge country, but much bigger than England, but they were scattered over a big range. And the people in Alsace-Lorraine always were trying to cheat the people in Normandy. They were cheating the people in Brittany. They were cheating the people in Paris. Everybody hated the Parisians, you know. So all the different factions were always against each other, so they would cheat on the systems. They had a system, but they would change the thing, trying to cheat the other guys. And it just became chaos. Now, does anyone know what happened around late 1700s? Name a few things that happened around late 1700s. That's a little before then. What happened in America? Yes, in 1776, right? And what followed very shortly? The American Revolution, the French Revolution. Now, actually, for revolutions, the American Revolution went fairly nicely. A lot of people got killed. There was a lot of really tense times, bad times. The Washington's troops at Valley Forge was an awful time. We came really close to losing it there. And the French helped us. Lafayette, many of the others came over and helped us because they believed in this. They had a monarchy that had gone haywire. They were just rich and luxurious, and the French people were suffering like crazy, and that's why they lost. But you see, we were new country over here, independent, lots of people thinking and putting into the system. We tried democracy. Now, the Athenians had tried it much earlier and seemed to work okay, but they didn't get it to sustain, so it fell apart. We tried it really and made it work. And we had, Articles of Confederation really didn't work too well. Then we went to the Constitution. That worked much better. It still is working pretty well. So we really came up with some good things. The French, though, when they overthrew the monarchy, they were so angry, so out of control. They just started chopping off heads at random. And it was chaos. It didn't go over too well there. They took, I'd say, hundreds of years for them to come back to an equilibrium. It was a pretty bad time there. But at that time of upheaval, they said, let's get rid of this stinking system that has us divided and come up with something better. The scientists were pretty much together then. And they said, well, let's take something that doesn't depend on anybody's body parts. Okay? By the way, this, anyone know what this is? Tip of the finger to an elbow. A cubit, exactly. If you read the Bible, like the building of the ark, Noah's ark, so many cubits plus cubits, that's what they're talking about. It's about 18 inches, a foot and a half. Okay? So yeah, there were body parts all over the place. Okay. Anyway, so they decided, let's take it away from that. So let's take it to something that is common everywhere. So they came up with a unit for length, the meter, which means to measure, by the way. That's where they got the name, not very creative, to measure. Okay? They said, let's take the distance from the North Pole to the equator through a line directly from there to Paris. Now, how in the world did they do that? I'm not sure. But they theoretically did that. And let's divide it into 1/10,000,000th of that, or something like that, and call it 1 meter. So that gave a standardized unit of length, 1 meter. Happened to be a little bit longer than a yard, but they didn't use this as the measure. They used that measure. That was fixed. That was immutable. Okay? And then from there, they divided everything by tenths, or multiples, tens, and actually got it up to thousandths, or multiples of thousands. And they built the whole system based on that. Not 12s and 16s and 3s and 2,000, 5,280s or any weird numbers like that. Everything was a power of 10. Well, so they took a meter, and to a hundredth of a meter was then called a centimeter. And a centimeter, 10 centimeters by 10 centimeters by 10 centimeters, that was 1,000 cubic centimeters. And they said, oh wait, I'm sorry, go back. Let's do 1 centimeter by 1 centimeter by 1 centimeter. 1 cubic centimeter of what's the most common substance on the planet, on the surface of the planet? Water. 1 cubic centimeter of water. They said, let's make that a standard unit of mass and call it a gram. So okay, by the way, a centimeter is about the thickness of your little fingernail. So it'd be 1 centimeter by 1 centimeter by 1 centimeter, something like that. Like some of those little bitty sugar cubes that don't sweeten anything, that would be a cubic centimeter approximately. And that would make 1 gram of water. Okay, so that's where they came up with a gram. Well, that was so very tiny, so let's say, well, let's take 1,000 of those, and kilo means 1,000. So a kilogram became the SI standard for mass. Now, no one wanted to mess with time, so we kept time the way it was. Same way it was in English, it was in French, it was everywhere. They kept the seconds. And seconds is the one thing that's not very metric, is it? How many seconds in a minute? And how many minutes in an hour? 60. How many hours in a day? 24. How many days in a year? 365. And a quarter approximately. The reason for that is time is measured by the solar system, the spinning of the earth. You can't do much with that. You can't make that metric. And by the way, those 60s, anytime you see 60s there, think Sumerians, the people who were there before Babylonians. The Babylonians were the people who were way before the Iraqis. But in the Tigris-Euphrates Valley, the Sumerians, they had a base 6 or 60 system. That's how you got 360 degrees in a circle. Anything with 6s in it, that's where it came from. So that's where those came from. We kept those. Now, electrical stuff, amperes, ohms, volts, watts, all those came way after this. Way after this. So everybody agreed to let's use the SI system. That's why an ampere anywhere in the world is the same as an ampere here. Volts, ohms, watts, all those things are metric. Kilowatts, megawatts, milliohms, milliamps, all those things are the same. Okay? So all the electrical things are the same here as here, because these all came way after 1791. Temperature, Kelvin. Not Fahrenheit, not Celsius, Kelvin. We'll talk about that in chapter 4. In chemistry, and we won't quite get there, quantity of matter is called the mole. And I wish we had time to get there, but we won't. And then one thing we don't do much on is light, and that's measured in candela. But these are the 7 basic units in the SI system. Now, most of these are the basic units like meters, seconds, amps, Kelvin, moles, and candela. The only one with a metric prefix is kilogram, because the gram was just so small, the way they defined it. Okay? But those are the 7 basic units in the SI system. Now, if we tried to compare that to the English system, basically our basic unit of length in the English system is the meter, not the yard, is the foot, not the yard, but the foot. How about mass? What would be equivalent to mass? Say again? A little while.
Cubic inch.
Okay, yeah, okay, that's a volume measure. But mass,
Will it be equivalent to
the kilogram. Say again? Okay, when you go to the grocery store and weigh things, either is measured in kilograms or ounces or pounds, right? But guess what? Those are completely different things. Kilogram measures mass, pound measures weight. Weight is not a kilogram. That's a mass. We'll talk about this later. We'll get there later. We do have a unit for mass in the English system, but I bet you none of you have ever heard of it before. Or if you have, you've already forgotten it.
the pound.
Huh?
The pound.
No. It's a slug. Did you know there was a unit called a slug? That is a unit of mass in the English system. Okay? Yeah. It's not a plug. That's true in the back. It's a slug. Oh, no. Okay. Okay, it's a slug. No one ever uses it. Okay? That's why you've never heard of it. We use weight. We don't use mass. But they're not equivalent. Weight in the SI system is Newton, which is not one of the basic things. That's a derived unit. We use pounds. Those are equivalent to newtons. But on the grocery store or in scales, the ones we'll use in lab, they'll have, some of them will have pounds and grams. Yeah, they use kilograms, don't they? Yeah, because that's what we've gone to. But back when I was young, they were still doing it by pounds. Yeah, they have changed. Everybody's changed to SI, except us. Okay. Even the English don't use, say again? Oh, yeah, that's it. Yeah. All right.
We're trained setters, not trained followers.
On this one, we're behind the curve on this one. Maybe most of the others, but on this one, we're behind. Okay, so let's look at these standard units and the various fundamental properties. First fundamental property was length. Now, you might think this is a weird way to measure length. But this is how they do it in the SI unit. This is actually the definition. How far light travels. Did you know light travels at a certain speed? Yeah. It's awfully fast, but it's not infinite. It's extraordinarily fast. Anyone know what it happens to be? Say again? Okay, it has to do with that. 186,000 miles in 1 second. 186,000 miles in 1 second. That's pretty fast. That would be 4 times around the equator in a second, or something like that. It's really fast, okay? So, the standard distance of length, rather than the distance from the North Pole to the equator, is what they first said, but how far light travels in 299,792,458 of a second, okay? That's a very short time. Who can measure that? I don't know. But that's how far light travels in that. It's 1 meter. Weird way to express it, but that way is as precise as any way we know. The mass. Okay, let's see if there's a picture here. No, there's not. Let me see if there is in your book. In some of the earlier editions of the book, they actually had one of these. It had a picture of that standard unit of kilogram. It's kept under a hermetically sealed glass thing. No air is allowed to get around. The fixed environment is there, held at a constant temperature and pressure. And that's inside another glass thing, and that's inside a vault inside the Curie Laboratories, no, the Pasteur Institute in Paris, France, where they came up with this thing. And that's where it's kept, and no one touches it. No one gets near it. What they've done is copy it. Sometime in the past, they made copies of the copies of the copies. That is the reference to that standard metal cylinder kept somewhere in the basement, somewhere in Paris, France, in the Louis Pasteur Institute, I think, or somewhere like that. Time. Time is referred to not circling around the globe and that kind of stuff. They've taken the oscillation of the cesium atom, which is a radioactive atom, and they can measure its oscillation very, very precisely. And so many oscillations, that's millions of oscillations of that, makes 1 second, or something like that. Weird ways to do it, but they've done it. Charge, we'll do that in Chapter 8. All other properties basically are derived from the other. We're not going to do candela. We're not going to do the chapter on light, which I think is Chapter 7 or somewhere there. Sorry about that. We won't have time. But we will get the others we need. But everything else, like forces and volumes and areas and energy and just about everything else are derived from those 7 we saw before. Yes, it really does. I think what we call atomic clocks, it may be based on cesium atom, but usually we use something more common like, what is it that quartz, the vibrations of a quartz crystal, okay? That's a lot. You don't want to wear cesium around because it's radioactive, but, quartz is not. So, I don't know. They do use other things, but yeah, that maybe atomic clock does use that, but they can use other things besides it that are very close to the same. Okay? So we have gotten very, very precise, much better than distance from the North Pole to the equator. That's a tough one to make. So here are those 7 basic units written in a table for us. Length in the in the metric or SI units. These are SI, System International System. Is the meter, okay? In the U.S. customary, that would be a foot. The symbol for meter is little m, okay? Symbol for foot is FT. Mass, kilogram. We don't use gram because that's so small. We use kilogram, which is 1,000 of those little cubic centimeters that we have of water, and that would be kg. K is the metric prefix, G is the basic unit. Time would be second, and we use the symbol second. And that's both. And by the way, mass in the U.S. customary is slug, which we don't use. In fact, slug is never used, so they don't even have an abbreviation for it. If you ever use slug, you have to write out the word SLUG or SLUGS. They don't have an abbreviation for it. It's that seldom used. Time is in second in both U.S. customary and SI. Electric current is ampere. Why is that capitalized and these were lowercase? Did they mess up here? Say again? It's the capitals that mean something else. What does that mean? Say again? Okay, it's electricity, yeah, but why is that capitalized unit rather than lowercase like these? Named after somebody. Meter was named after the verb to measure, okay? Gram, I don't know where they got that. K is just a prefix. Second, I don't know where they got that. But ampere was named after Louis Ampere, a Frenchman who studied current. So that's why it's capitalized. Okay, temperature, Kelvin. In U.S. customary, we often use degrees Fahrenheit, but Kelvin is the SI unit. It's a capital K. Wonder why. Okay. But not somebody's name, somebody's title. This was William Thomson, who did a lot of the work in thermodynamics, okay? But he was not only named William Thomson, one of the few of the English aristocracy that was also very smart. Most of those landholders were inbred too much and they weren't very smart anymore, but they were very rich. He happened to be Lord Kelvin. He was a lord. He was up there in the aristocracy, but he was also brilliant. and his title was Lord Kelvin, so we named it Kelvin after him, after his title. Amount of the substance, mole, that has some word somewhere. And since they already used little m for meter, they had to use MOL for mole. Why didn't they just put the E on it and have it mole? But they put it MOL. And luminous intensity was candela. I don't know if something had already been named D or C. C certainly wouldn't work because that's the prefix for centimeter, so they use CD. So, who uses that anyway? People who study light, but we're not going to. So, the main ones you need to know for the first several chapters is length, mass, and time. When we get to chapter 4, you'll include temperature. When we get to chapter 6, we'll use electric current, and we won't quite get far enough. But in chapter 8, we'll get close to talking about moles. We might actually get there, may or may not. We'll try. Okay. So, we talked about the problem with the U.S. customary or English system is none of the unit conversions make a lot of sense. I mean, they make sense, but they're all over the board. They're no systematic thing. In the metric prefixes, they all make sense. They're all powers of 10, and they're the same. A kilometer, is 1,000 meters. What's a kilogram? 1,000 grams. What's a kiloamp? 1,000 amp. What's a kilo ohm? 1,000 ohms. It means the same thing no matter what you're measuring. So you don't have these different things. You always use the same thing. Simplify the conversion process because you can either use the symbol or you can use a power of 10, whichever way you want to do it. And here's how you do it. Let's say this is too short for a meter, but if that was a meter, divide that into 10 equal pieces, and that makes a decimeter. Think decimal. A decimal is 1/10 of whatever. You know, one decimal place is a 10. So that's a decimeter. Then if you divide that decimeter, let's spread that out to here. That's longer than a decimeter. And divide that into 10 equal pieces, and what do you have? A centimeter. Okay. Now, centi means 100. 100th of a meter because it's a 10th of a 10th. It's 100. What do we call this? A penny. And what's its value? 1 cent. Why do we call it a cent? It's 100th of a dollar. Centidollar. It's a cent. 100th of a dollar. Second? Yeah, we did. Okay. Now, what do we call 100 years? Century. Okay. No, a decade is 10 years. Okay. Close, but no cigars. Okay. A Roman centurion had about how many people under his command? 100, approximately. Okay. Yeah. So that's what centi has to do with 100. Okay. A centipede, 100 legs, he calls it. Really doesn't, but a lot of legs. Okay. Then you take a centimeter, which is about the thickness of your little fingernail, and spread that out some, and divide that into 10 equal pieces, and what do you have? A millimeter, which is a thousandth of a meter. Okay, it takes 1,000 dimes in to make 1 meter. Okay, so that's your millimeter. Now this is powers of 10. 10, 10, 10. Okay? But when you go smaller than this, they don't do tenths anymore. They use powers of 1,000. 3 tenths. So this would be 10 to the minus 3. The next one would be 10 to the minus 6, 10 to the minus 9, 10 to the minus 12, 10 to the minus 15, 10 to the minus 18. We usually don't go too much beyond that. Okay? So, the metric prefixes simplify the conversion process. Everything's a power of 10, whether it's 1 power of 10 or 3 powers of 10. Avoid writing large or small numbers. Rather than writing 1,742 millimeters, we write 1.42 meters. Okay, it just makes things easier. Or rather than writing 0.000 meters, 0.1 meter, you'd write 1 millimeter. Okay, so it just makes it easier to deal with rather than carrying all those decimals or all those zeros, you can just use an either bigger or smaller unit. Okay? Now, I've sort of gone through things maybe a bit too fast. Let's just see. Backing up just a little bit, looking at some of the other measures. 150 miles they chose in your book. This is figure 1.4 in the book. 150 miles. Now, can you think of anything about 150 miles from here? What? Second? Really? About 150 miles. If you went east from Birmingham, you'd be in Atlanta in about 150 miles. That's about 150 miles, okay? So, yeah. Here to where in Mississippi? Oh, you're at what?
Yeah, I'm in.
Oh, you're in Florida. Okay, northern Florida, I bet.
I'm
Yeah.
a little bit over 100 miles.
A little bit over 100, so you're not quite as far. Okay, but let's just picture 150 miles. Birmingham to Atlanta, say, 150 miles. Or here to your home, 150 miles. That would be about, have you ever measured it in leagues? No, probably not. 50 leagues. So it's about a third of, no, a league is 3 miles. Yeah, a league is 3 miles. A mile is a third of a league. Okay. Yeah, you were thinking Jules Verne's, right? 20,000 leagues beneath that, yeah, something like that, yeah. Under the water, yeah. 130 nautical miles.
In the water.
Huh? That's surface of the water. Okay, what's the difference in a nautical mile and a mile? Does anyone know?
Nautical miles long, right?
Longer, yeah, for sure, because there's only 130 nautical miles and 150. They're the same length, but a mile is how many yards? No, that's feet. 1,760, whereas a nautical mile is 2,000, exactly. It's a bit rounder number, okay? So that's 150 miles or 130 nautical miles. If you were in Rome back in the day, it would have been 158 Roman miles. Now, I don't know where that came from, but okay. If you were a horse, that would be 1,200 furlongs. Okay, remember the Preakness and they're measured in furlongs. Okay. If you're doing surveying of land, that would be 1,200 chains. Did you know all these units were out there?
What are these considered? Are they considered metric or?
No, this is old units from somewhere else. Probably somewhat English, but just different fields of measurement. If they use something, that's too long, that's too short, they pick something that they wanted to use. Like surveyors use chains. Because probably they could carry a chain of that length and not be too heavy, so that would be a chain. But it was very well defined. But if 4 rods made a chain, so that'd be 48,000 rods, okay? A shorter unit for measuring, okay? Or cubits, that would be 452,571 cubits from Birmingham to Atlanta, or 792,000 feet. So you see, you could use all sorts of different reference, and they would be all over the place. Metric system's a lot easier. Okay. All right, I think we caught up to where we were. So, a little bit more. Okay. Before we get to this, we've already talked a little bit about this. Basic unit of length, metric system. Meter, okay? Meter. What if you did 1 meter times another meter? That would, and by the way, here's another measure for a meter, okay? Most doorknobs, strangely enough, are about a meter off the floor. A little bit more than a yard, that's approximately a meter, okay? Now, since the distance from the floor is almost the same as the width of the door here, that's close to a meter. Probably not quite, but close, okay? So what we would call the area here, there. It would be 1 meter by 1 meter, we call it 1 square meter, exactly, okay? So if you're measuring area, you multiply length times width, that gives you a square meter, square centimeter, square feet, square yards, square miles, square kilometers. I mean, any length measurement, you can measure length by length and you get square length. What if, and by the way, if you're putting towel on the floor, if you're bidding on this, you would measure the length and the width, multiply them together, and get how many square feet, and that tells you square what. This is about a foot, wouldn't you say? And that's about a foot, so each of these is 1 square feet, so 1 square foot. So if you were ordering tile this size, you would get that many tiles. Multiply the length times the width, get a number, and that would be how many tiles you would need. Now, sure, there's some angles cut out here or there, but that's a good estimate, okay? So that would measure that. What if you're trying to figure out how much air is in the room? Cubic feet. Usually feet by feet, the area times the height. And this, by the way, is pretty, ooh, gracious, I'm going to kill my computer here. This is about what? 8 inches, yeah. So another 4, that would be about a foot. So you measure every 1.5 block from the top to the bottom would be how many feet tall the room is. And I'm just guessing you it's about 9 feet, would you say? Because I can reach about 8, but not quite. Is it about another foot? That's about a 9 foot ceiling, would you say? About. So the area of the floor times height, that would be cubic feet, cubic centimeters, cubic meters, cubic whatever, okay? Just another thing. Those are called derived units based on the unit for length, okay? Now, what they don't have in the text, and I wish they did, in the slide set, is a table on metric prefixes. And only a couple of you have books. So I'll go over those just to record them here. When you get the books, look at the table. We'll start with a unit, like meter. Basic unit meter. Now, we've already started going down from that to smaller units. So a tenth of a meter is a decimeter. A tenth of a decimeter is a centimeter. A tenth of a centimeter is a millimeter. Okay, so you get smaller, smaller, smaller. Now, and we went by 1 power of 10. Now we go by 3 powers of 10. So you go from 10 to the minus 3 to 10 to the minus 6. What would we call that? Micrometer. Okay, now wait, let's get our units on here too. Okay. Decimeter would be a DM, decimeter. This would be a cm, centimeter, and this would be an mm, millimeter. Okay? Pretty straightforward. If you did, that's 10 to the minus 3 meters. If you went to 10 to the minus 6, that's micrometer. Okay, now wait a minute. Micrometer. How are we going to call that? We've already used little m. Oh, you use that funny looking symbol for micrometer. You've probably seen this before. Does anyone know where that came from? The what? Say again? Absolutely. You know which language? Greek to me. Yeah, it's Greek. The Greek symbol for the little letter m is called mu. This is the lowercase mu. That's where that comes from. The lowercase mu. Okay? Micrometer. We sometimes call it a micron, only that's a millionth of an inch, I think, is a micron, isn't it? Okay, anyway. That's 10 to the minus 6 meters. This is 10 to the minus 3 meters. This is 10 to the minus 2 meters. This is 10 to the minus 1 meter. Okay? Next one down would be 10 to the minus 9 meters. What do we call that? Nano. 9 nano, that makes sense, sort of. Oops, sorry, I can't write. Well, I'll put it here. Nanometer. Okay? Now, what are we down to now? Okay, let's go back to our dime here. Okay. You know, okay, in this class, because it has a lab, I have to call roll twice. I was supposed to call it at 3:45, and nobody told me when we reached 3:45. So shame on you. Yeah. Okay. Here's my pen. So let me mark the roll for the lab period. Okay. James. Okay, I'm still trying to learn names and face. Terrence Michael Birch didn't show up today. No one knew him. You're the Jacob with two. You're Camp, right? Sleeping Camp. Okay, never mind. Got him. So you're Slim, and Dart isn't here, right? Okay. Mason was this. Okay, I'm still learning names and faces. Samuel. Okay, over there. All right. Ryan. Okay, thought that was you. Alfred. Which one? Okay, I'm sorry. Jeremy. He was here, yeah, but he was here before, so fine. He was here at 3:45. Jalen Keeman or Kimon or something like that. Roby, no one knows him. Okay. Charles. Okay, good name. I should remember you. Okay, Brittany. Was she still here at 3:45? I think she had to leave at 4, so I guess I.
Somebody left.
Huh?
Some girl left.
Yeah, that was Brittany. Trevor. Okay. And Terry, I think he just recently left. Well, I think he was here at 3:45, wasn't he? Yeah, the guy that was here. Yeah, he was still here at 3:45, wasn't he? It's now it's 4:45, so I think he didn't leave more than an hour ago. I forgot to call roll when I was supposed to. Okay, so let's get back to this. A millimeter is about the thickness of a dime. So if you slice that into 1,000 equal slices, slice that dime into 1,000 equal slices, you can always see through this, right? That would be a micrometer, okay? Now, slice that into 1,000 equal slices. I can't even imagine that. You're down at nanometer. And when we talk about nanometers, you're talking about the width of an atom. I mean, you are, a second. And you may have heard of nanotechnology. It's talking about down on this scale. Atomic scale. Really, really, really small. That's 10 to the minus 9. Do we stop there? No, we go 10 to the minus 12. That would be a picometer. Now, second? Yeah, okay, you're going bigger. Okay, this is going smaller. Now, the only reason I know or remember anything about pico is that before I started working here, I worked at Southern Research Institute in Birmingham for about 8 years doing radon research. And radon is a radioactive gas in very, very, very small quantities that can still do damage. Yeah, it comes up through soil. Yeah, exactly. Okay? And people's basements sometimes get high in radon. And it's the second leading cause of lung cancer after smoking. Smoking is the big one. After that, radon is number 2. But because it's naturally occurring, you can't sue anybody, so they try to fix houses they know with high in radon, like my wife's sister's house was high in radon in Huntsville, but they treated it, I went up there and helped them treat it and knock down the counts for a while, but then they brought in, Well, they had a big crawl space, and the crawl space was exposed soil and it was coming through that. So they covered that with layers upon layers of visqueen, polyethylene sheets, thick stuff, and taped that up the walls so none of that soil gas got in, and taped it between the sheets, trying to keep it all under there. And radon is radioactive. That's where it causes problem, but it'll decay away in every 4 days. But it's always being produced. But if you can keep it under there for 4 days, it's going to decay away and become a solid again. See, it's a gas when it's radon, but when it decays, it becomes a solid and goes back into the soil. You could, yeah, and the rest of their basement is covered with a slab, but even in the slab, there was a crack, expansion crack between the wall and the edge. So they filled that with polyethylene caulk that sealed that really well. But then still, the radon gas get in the concrete block, the holes there. So what they did there was put a ventilation fan and suck the air and blow it to the outside. And they got rid of most of the radon. And actually, when I was at Southern Research, we developed many of those techniques. But the company they had did use the techniques we had done, but they were professionals at it, and they knew exactly how to do it. But, so it was sort of nice to have had a little bit of hand in that. Okay. Anyway, so radon, just a little bit of it can cause you problems, and you measure radioactivity in Curies, named after Marie and Pierre Curie, the husband-wife team, the Nobel Prize winners, because they first discovered radium and that it was radioactive, and unfortunately they died of cancer because they were exposed to radium, which caused cancer. They didn't know it, but they were. So it's called Curies, and a 10 to the minus 12 Curies is a picocurie. And if you're exposed continually to 4 or more picocuries of radon consistently, you could get lung cancer. It increases the risk of lung cancer. So that's a very small amount. But fortunately, you can mitigate that. And if you're outside a lot, you're out that. But if you're living in a basement that is in a radon-prone area, you might want to have it checked. Okay. But we get smaller than that, 10 to the minus 15, the next power of 3 down. And what would that be called? Femtometer. That would be femto 15, 10 to the minus 15. And then I think they go down to 10 to the minus 18. And is it AXO or something like that? Atto, okay? And that's an attometer. Now, I don't even know what is that small. I mean, if an atom is about a nanometer, maybe a proton would be a picometer, and maybe an electron would be measured in femtometers, maybe atometers. I mean, you're talking so tiny, I can't even imagine that. Okay, let's go on the upper end. What if we had, and then we had meter, that's just a meter. What if we had 10 meters? 10 meters would then be called what are 10 years called? Deca. So that is, and some books use DCM because they already use DM for deci. Some use DKM. Which does this book use? DK, isn't it? No, DA. They use DAM. Okay. Sorry about that. I've seen it. Well, no, they don't use DCM. It's D. I don't even think DAM. Decameter. Okay. Okay. Then if you had 100, what would you call that? You want to know that? Hectometer. Think 100 hecto. Okay. Now the main way I remember that one, okay, in the U.S. in our system, if you're buying land, area of land, what do we usually buy it in? Acres, exactly. And acres is so many square feet. Now, I don't remember exactly, 5,000 or some, 500 and some square feet. Anyway, it's a big area of land. A football field is, pretty close to an acre, I think. Okay? So it's quite a few square feet. And that's what people were used to measuring in. Well, when you got to the metric system, a kilometer is a lot bigger than that. So a square kilometer was too big. And a square meter, of course, is way too small. But what would be close to an acre in size, not the same, but close to it, would be 100 meters square, which would be a hectometer square. Well, that's a lot of syllables there, so they sort of abbreviated that to call it a hectare. And that's how they measure land area in the SIU countries, which is all the rest of the world except the U.S., is hectare. Not acres anymore, but hectare. A hectare is a little bit larger than an acre, but that's how we measure. If you read in agricultural journals and things like this, they'll talk about so many tons of corn per hectare, not per acre, but yeah. So that's how they measure things there. 100 meters, hectometer. 1,000 meters, you know that one? That's kilo. 1,000 means kilo. Okay? Then we go up by powers of 3, so that's 10 to the third. So 10 to the 6th would be mega. Megameter. But wait a minute, we've already used our little m for milli, and then we had to go to the Greek alphabet, the little mu for micro. What are we going to use for mega? Why not capitalize? It's a big unit, isn't it? So let's use a capital M. So this is a megameter. Okay? Capital M, little m. Okay? 10 to the 9th. Say again? What'd you say? Giga. Okay, think of your computers now. After you talked about, I can remember when they used to brag about these new laptops they came up with. Yeah, they would go so many kilohertz or so many kilobytes of memory. And they say, boy, this is really big. Well, no one measures them in kilo anymore. In no time, they went to mega. Like those, remember those floppy disks? They were 4 megs. Ah, that's okay. Well, now we don't measure megs anymore. What's next? Giga. Yeah, we're up to gigabyte or gigahertz. And since we went to capital M, we go to capital G. Huh? Yes, exactly. So the next one up, 10 to the 12th, is tera. And since we went to the capital M, we do all capitals for now. That would be terameters, okay, or terabytes or terahertz or whatever. And 10 to the 15, that's ugly. I mean, is what? Peta? Is that what you say? Okay, I never know how to pronounce that one. If it's prevention of cruelty to animals or something like that, that's PETA. I don't know if this is PETA or PETA or what, but I can't get my pen to work. 10 to the 15 is capital P, petameter or pega, whatever. And let's go on to 10 to the 18, exa. Okay, I should be writing these out because y'all don't have your book. This is giga, G-I-G-A. I will leave off the meter. This is tera, T-E-R-A, right? Y'all correct me if I'm wrong. That was P-E-T-A? Yeah, P-E-T-A. Which is convenient because we had a little p down here, now we have a capital P here. And this is exa, E-X-A, isn't it? Yeah, E-X-A. And that's as high as I care. In fact, I never use those things. Basically, we'll stay within micron, not often, but occasionally in micron, and then we so far gotten up to tera. I've never used it bigger than tera. In fact, only recently have we ever started talking about terabytes or terahertz or something like that. Okay, so I wanted to get that one because that was in the book and not here. Okay, the next one that we didn't do, though I did mention it, what if you had 1 decimeter? So let's say this was a decimeter. I'm going to erase what I've got so far. Okay. And so we had another decimeter high. I don't have enough room to make it decimeter high. But then say we also were a decimeter deep. Okay. Okay. And we had a cubic decimeter. Okay. Now, we know that if that's a decimeter, each one of these would be a centimeter, right? So this would be 10 centimeters by 10 centimeters by 10 centimeters. Length, width, and height. So that would be 10 by 10 by 10 is 1,000 centimeters cubed. You got it. 1,000 cubic centimeters. Anyone want to know, have an idea what 1,000 cubic centimeters is? Could you pick up the bottle that's behind you? I don't know if it belongs to anyone here. Okay. Now, can you read how big that bottle is?
How big the bottle is,
How much it carry? It held.
20 fluid ounces.
How much?
20 fluid ounces.
20 fluid ounces. Does it have anything in parentheses?
1.25 pints of PT.
Pints, okay. It doesn't have any other thing? Say again? 591 milliliters. 591 milliliters. Okay? Which means the next size up that you could probably buy in the store, they don't do them in ounces anymore. They have, say again? Liters, 2 liters, and 3 liters, right? So 1 liter would be not quite twice that, okay? Not quite twice that. That's a liter. This is a liter. This is 10 centimeters by 10 centimeters by 10 centimeters. That'd be 1,000 cubic centimeters, which would be 1 liter, which is 1,000 milliliters, right? Because milli means 1,000. So 1 cubic centimeter is the same as 1 milliliter. Okay. Now, what did we used to measure in cubic centimeters? And maybe some people still measure things. They do. I know they do. Say again? Perimeter?
Like shapes.
Okay, it's capacity is what you call it. It's usually liquid capacity or something like that, or fluid capacity, volume, exactly. But not volume as in, yeah, okay. Yeah, and it is cubic centimeters, okay? Liquid capacity or volume, okay? In fact, there was a car named after this. They picked a weird way to name it. They mixed all sorts of weird things that were nothing in their culture, okay? It was a company that used to make motorcycles. That's what they were known for. And then they decided to take their biggest motorcycle engine and put it into a car body and try to make it work. And it was a little underpowered, but they named that, yeah, say again? No? You're in the right country, though. Okay? I believe it was 104 cubic centimeters. Now, they used to call a cubic centimeter a cc. I grew up, my mom was a nurse, and she always referred to medicines not in cubic centimeters, but cc's. So many cc's of this or cc's of that. They've gotten away from cc's now. Hey, you're getting close. Does anyone know what 104 in, strange enough, Roman numerals? Anyone know what 100 is? Okay, how many soldiers did a centurion have under his command? 100. So let's say C, century, centurion, C, Roman, okay? And 4, anyone remember what that was? IV, okay? CC, a Honda Civic. I heard, I don't know if this is really true, but I heard that's where they got the name Civic.
When they first came over, they had CDs.
Yeah, little bitty things.
When you put in a car, high boost motor, they put in smart cars.
What's that now?
They put the high boost motor in smart cars.
The what kind of motors?
High boost.
Oh, really? Okay.
The sport bike.
Yeah.
Well known to be the fastest sport bike there is.
Oh, really?
Those are smart cars. They'll actually demolish.
Had to do a little bit of gearing on it, though, probably, but yeah.
Well, that's a 1300 cc motor that he's talking
Yeah.
Okay.
That's a little bit bigger than 104.
Okay.
It'll move that little car along.
Okay. So that, and I don't know if that's true, but that's what I heard. It's where they got the name Civic, was from CIV, Roman numerals, the Japanese using Roman numerals, and then CC. Yeah, okay, fine. But that's where they got the name Civic. I don't know if that's true, but that's what I heard. Huh? I can't hear
Or
it.
it could just be a huge coincidence.
It could be, yeah. Okay. Now,
Yeah.
and by the way, if y'all haven't noticed, I am hard of hearing, so it's not I'm being obnoxious or something. I just can't hear well, so I will ask you to repeat things too many times. Okay. So, by the way, what this gets to is 1 liter, like that 1 liter Coke you buy or whatever, Mountain Dew, Dr. Pepper, whatever, is 1,000 cubic centimeters, or 1,000 milliliters, which makes a milliliter the same as a cubic centimeter. And nowadays, in drugs, they went from cc's to cubic centimeters, but then they now measure them in milliliters. If you're giving your kid, eardrops and stuff, usually they'll tell me how many milliliters to get. Okay, so all those are connected. Yes.
What about medicine that's got like a aspirin that's 200 milligrams?
Yes. Okay, that is a mass because that is a solid. Liquids are in cubic centimeters, or cc's or milliliters, whereas mass would be in grams. And yeah, if you take an ibuprofen, isn't that usually the dosage there, 400 cc's or something like that? You'll always see that. Now that's the actual dose. It's not the pill. The pill has other filler in it, cellulose or something, just so it's. If they gave you really just that much, you would take too many out probably. But so they put them in a pill, which is normal size. But you only the dosage that you're taking is how many milligrams of actual medicine is in that. Yeah, that's exactly right, because that's a solid. They're measuring mass. Liquids, they measure volume. Good point there. Okay, and by the way, what is a liter close to in the U.S. customary system, the English system? Say again? A quart. It's very, very close to a quart. If you had a quart of milk and poured it into a liter Coke container, you come up a little short. If you took a liter Coke and wanted to pour it into a quart milk container, you'd spill some out. They're very close though. Now I can remember, see what year that would be. I graduated from college in 73, so this would have probably been 70. Yeah, the summer of 1970. I went on my first midshipman cruise. I was in Navy ROTC, and it was end of my freshman year before my sophomore year. And I was pretty lucky. I got on a ship that went across the Atlantic to Rota, Spain, and then before they went to the Mediterranean, boo hiss, they put us on another ship and came back across the Atlantic, back to Little Creek, Virginia. But we were in Rota, Spain for a short period of time, which is a Navy base there. And I remember they put us on the bus. They were going to take us to the other, someplace to wait for the other ship to come in. Yeah. Oh, yeah, absolutely. Okay. Yeah, the rest of it will be here. And if you need the math, this is being recorded, so get down there to math. Okay? But if you're acing the math and want to stay here, y'all work it out. Okay.
I'll definitely let you know what they say.
Okay. Yeah. But what you have to do is make up labs and tests, We'll work it out. Okay. So this was back in 70. I don't know if y'all weren't alive then, were you? No. Okay. You were. Okay. 4 years old? All right. Rub it in here. Okay. All right. I don't know if you remember, you wouldn't remember if you've read about it. That was when gas prices were beginning to really go up. Okay? Because I remember when I was in high school and at first driving at 16, y'all may find this hard to believe, they would have gas wars sometimes, especially in small towns and places like that. And when they had them, they usually would get down to, this is hard to believe, 19.9 cents a gallon. 19.9 cents a gallon. $1's worth of gas would get you 5 gallons of gas, plus a little bit. Okay. So, boy, those were the days, huh? Yeah, you can't go very far on that. I could put $1's worth of gas in and have more in the car when I took it home than when I went into town. Okay, by a long shot. So, By the time I was a freshman in college, however, the gas prices were beginning to go up. And if my memory was right, they were pushing $1 a gallon by then, and probably close to $1.20 or something. It was right in that range. So we got over to Rota, Spain, and I don't know if y'all realize it, if you've ever traveled outside the country, we still pay way less for gas than the rest of the world do. Way, way less. So we got over there, and I was on the bus. They were driving us through the base there, and we happened to pass a gas station. I don't remember what brand it was. Maybe it was off-brand, I don't know. And I happened to look up to see what the price was. You know, it was there listed. And it wasn't much different from what we had paid in the States. I said, oh, of course, this is a Navy base. They probably pay the same amount. And I said something to someone, and he said, no, look at the thing. That's how many dollars per liter, not dollars per gallon. It was dollars per liter. It's about a quart, so it's about 4 times what we were paying in the state. And this was on the Navy base. If you went off in the economy, it was more than that. Okay? We have it pretty good, folks. Okay? We always have. We really, our prices are subsidized by the government. Believe it or not, they are. Or not taxed as much as others. You know, however you want to say it. And they're still taxed quite a bit. So I don't know what they are in Canada or Mexico or Europe now, but it's a lot more than what we pay. Huh?
We'll pay some in Mexico.
Yeah, well.
Before we can pay some, assuming it's really cheap in Mexico.
Yeah,
The dollar's worth way more than the peso.
oh yeah, way more.
We'd be doing that.
Actually, another story and this has nothing to do with this that I was talking about, but my wife's family used to like to take pretty nice vacations, not every year, but pretty frequently. We went a couple times up to Canada. And I think the first time we went up to Canada, her mom prides herself on being quite a shopper. And of course, the US dollar was a lot more valuable than the Canadian dollars were. So they had made the exchange there. And no, but they hadn't changed all of them, but they were used to exchanging them. So she went in to buy something in the thing, and she was paying with American dollars, and she was buying something that, let's say, was 15 Canadian dollars, but when she paid for it, she got a lot of change back. And she didn't realize the reason, because the dollars were different values. She came out of the store and she bragged to her husband, Karen's dad, and said, man, I made a killing in there. And he just laughed at her because he's an engineer and he knew that what was going on. No, she got ripped, probably both sides running, but she didn't realize the change of the rates. But anyway, my point is a quart in the U.S. system, very close to a liter in the metric system. Liter's a little bit more, quart's a little bit less. Okay. And that, by the way, is a liter, which is a little bit more than a quart. So finally, we get to go to understanding from the measurements. Okay? First thing we're going to do is talk about data in general. Data, of course, are numbers followed by units, always. Now, once you have data, those are measurements of things, lengths, widths, whatever, masses, temperatures, whatever you're measuring, that's your raw data with units after. Now, sometimes the units are pretty complex, meters per second squared or kilogram meter per second squared. Yeah, they can get pretty heavy. But once you have data, then sometimes data themselves, and by the way, data is plural. I don't know if you realize that. A single piece of information is called a datum, singular, whereas more than one is called data. So data are, not data is, okay? But you hear people misdo that all the time. All right. But once you get raw data, sometimes you get a lot more information if you start looking at ratios and comparisons of data. And usually when you say ratio, you mean a comparison in a division sense. And we've already talked about some of those recently, just a few minutes ago. What are some ratios that you deal with all the time? Say again? The conversion factors between SI, metric, and US. That's a ratio. Okay? Other. We just mentioned when we talked about gasoline prices. What do we measure those in?
Yeah.
So many dollars per gallon, right? Dollars value divided by gallon, dollars per gallon. And if you're driving in your cars, you measure miles per gallon, or how fast you're going, miles per hour, feet per second, cubic feet per minute. You're measuring ratios all the time. Ratios sometimes tell you more than just the raw data. They give you really good ways to generalize things. Okay? One ratio is the density ratio. You know what the density ratio is? What do we measure density in?
Air.
Second?
Air.
Okay, the density of air, that's what we measure. What units would we use to measure that? Okay, volume's involved with it, definitely. There's really two types of density. In the SI unit, we use mass density, and that would be kilograms per cubic meter, grams per cubic centimeter. That is a density ratio. Mass per unit volume. So the volume was right, that's in your denominator, the numerator is the mass. Now, since we don't use mass in the U.S. customary system very much, we use, instead of mass, we use weight, okay? We use weight per unit volume. That would be pounds per square foot, cubic feet, pounds per cubic feet, something like that. So those are density ratios. Mass density or weight density. In this book, we're using mostly mass density. Okay? Now, we'll get to that in a minute, too. Symbols and equations, that's how we relate these things to each other. We'll talk about a few of those, and then we'll talk about how to solve problems, which we'll do a few in this chapter, but in the subsequent chapters, we'll have several equations and how to solve problems, and we'll do those as we get to them in the text. So let's first look at the data. Here we have a cube, nice colorful cube too. And if this is really a cube, what's true about a cube? All sides are equal. And not only that, all the angles are equal too. Okay? And in fact, what are all those angles? Right angles, 90 degrees. Okay? So all sides are equal and all. So if you sat on that and made it squish like this, that would no longer be a cube. It would be a rhombohedron or something like that. Okay? But this is a cube because not only are the sides equal, but the angles are too, and they're all 90. We're not worried about the angles now, but that's what makes it a cube. So if all the sides are equal, we can give it some length, like S. So this is S this way, and S that way. Now because it's three-dimensional and two-dimensional board, these don't look like the same length, but they're going back into the board, which you can't really do. So what is the area of one face of this cube? If each edge is S by S, what would be the area of that face? S squared. And how many faces does it have? 6 faces. Front and back, top and bottom, left and right side. 6. So what would be the total area of that cube? 6x squared. So the area of one face would be, A would be S times S, S squared. And the area of the cube, the surface area of the cube, would be 6 times each face, and that would be 6x cubed, S cubed. Now what would be the volume of that cube? Length times width times height. Length times width times height. What would that be? If each edge is S, S times S times S, which would be S cubed. Okay? So those are data. The length of a side, the area of a face, the area of the whole cube, the volume of the cube. Okay? So data are the measurement information that you use to describe objects, like sizes, masses, whatever, conditions, like if this was moving, how fast is it moving? Is it accelerating? How fast is it accelerating? If it's moving, what force does it have? What energy does it have? Those are the conditions. What temperature is it at? You know, those would be data. It could be used to measure events, like how far did it go when it was moving? Okay? That would be an event. That's a strange one, but it could be changes. For instance, if this was expanding or changing temperature or doing something else, then we could measure the changes in that. So one example of describing the object would be the volume of it, the dimensions of the cube, which would include the areas, volumes, and various things like that. So, ratios and generalization. Let's think of those cubes, okay? Now let's think of a cube that's 1 inch on the side. What would be the area of one side of the cube? 1 square inch. And if you had all 6 sides, 1 square inch times 6 sides would be 6 square inches. Okay, good. What would be the volume of that cube? 1 by 1 by 1. 1 inch cubed or 1 cubic inch. Exactly. Now, what would be the ratio of the area to the volume? 6 to 1. Oh, they just put 6. Now, really, they should have units with that, but the units get awkward. That would be square inches per cubic inch. They really should put that, but they're just looking at the numerical ratio. Or, since this is inches inch and this is inch times inch times inch, you could say that's per inch, which is a rather strange unit. That's why they leave them off. Okay? Now, if that was 2 inches on the side, what would be the area of each side? 4 square inches. And how many sides you got? 6 times 4 is 24 square inches. What would be the volume of that cube? 8. So what would be the ratio? 8 cubic inches. What would be the ratio of that? 3 to 1. Look at that. Your size went up, your area went up, your volume went up, but the ratio went down. What if it was 3 inches on the side? What would be the area of each side? 9 square inches. And you have 6, 54 square inches. What would be the volume of that? 27 cubic inches. And what would be the ratio? 2 to 1. So as your size goes up, your ratio of the area to volume actually is going down. Okay? Now, it's a little bizarre, isn't it? This is a graph showing it, and to me, this is a rather bizarre looking graph, but here they've got the area, 1 unit, I assume that is, 6 square inches here, 1 cubic inch here. They're using the same scale for it. The area to volume ratio would be 6. Okay? That's a little over halfway there. Whereas if you had 2 inch cube, 2 inch cube, it would be 24, so it's a little over, not quite halfway between there. Okay? But the volume would be down here 8, just under 10, but the area to volume ratio would be smaller. It would be 3. And if you went up to a 3 inch cube, that would be 54 up here between 50 and 60. But the volume would be 27 here between 20 and 30. And the ratio would be even smaller, 2. Okay? So you see, as the size gets bigger, the ratios get smaller. Okay? Now, okay, all right. Enjoy. Okay. Okay. What are some ramifications of that? They give a few here. He left with his bottle, okay, and he left with his bottle, so we lost our bottles. So let's imagine it's summertime. That's a good feeling, isn't it? And you've been hot, working in shop, it's burning hot, you want a good glass of iced tea. Okay? So, hot tea, what if you put big cubes of ice in it, or you put crushed ice in? What difference is that going to make? Any?
Yeah.
What?
Keep those gonna last longer.
No.
Will do what?
If you got the same amount of ice.
If you have the same volume of ice. But you're sort of right. Why? Because the crushed ice is going to melt faster. It's going to get cold quicker, right? Like a slushy or whatever those things are. Those are really small pieces of ice. Those will hurt your head, if you drink them too fast because they're so cold, okay? The reason for that is you've got the ice in smaller and smaller pieces, but as long as you had the same volume of ice, the same amount of ice, but you had a larger, with smaller and smaller pieces, you had larger and larger surface to volume ratio. So therefore there was more area per unit volume, so that ice melted faster because the more contact it has with the hot tea, it's going to melt faster. A big cube is only going to melt around the edges. Crushed ice has lots of edges, okay? The volume to mass ratio is getting big. Okay? Mom ever make you peel potatoes?
Yeah.
She should have, okay? Do you like to peel big ones or little ones?
Neither by the choice.
Okay, but if you had no choice, okay, if you had to peel 5 pounds of potatoes, let me peel the big ones. Because the little ones you're going to be peeling all day before you get up to 5 pounds. Why is that? Because the larger the potato, the smaller the surface to volume ratio is. Just like here, the larger it is, the smaller that is, area to volume, surface to volume ratio. So to get the same amount done, it's going to take you a lot less peeling because less to peel for unit for a large volume. Okay. Examples of that. Now let's look at the density ratio. As we said before, density, especially mass density, is the ratio of mass to volume. Now, why would we care about that? Couldn't we just measure mass and compare masses? Well, we could. That just tells you how much of it you have. Or measure volumes and compare volumes. That just tells you how much space it's going to take up. But if you look at the ratio of the mass per volume, you can tell a lot more. Okay? Because this is an intrinsic property of the material. It doesn't matter how much you've got. Okay? Now, sort of the classic historical story of this, it's not clear whether it really happened, but it's been told often enough people think it did, and maybe it did. There was a very famous, he's a mathematician, a scientist, an engineer, man way ahead of his time, named Archimedes. Archimedes lived way back, BC, maybe 600 years BC or something, way back there, okay? But he was a man way ahead of his time. Very, very bright. And kings loved him because he came up with ways to battle bigger armies and navies and stuff with smaller things, and he could beat them because he thought of ways to do it. He took a big magnifying glass that focused on the sun, set it up where he knew the ships were coming, and they're wooden ships back then, focused it on them, and when they came in, it got so hot they started burning as they entered the harbor. I can't imagine that. Has anyone ever seen an auger that, you raise the say, when I was growing up on the farm, we used to take the grain off the truck and put it into the grain bin, the auger. You know what the name of that really is? Archimedes' screw. He came up with that concept 600 BC. He pumped water that way out of bilges of boats, He came up with incredible things. Well, one time his king, and I can't remember which country it was, Syracuse maybe, I don't remember. But his king, who he was working for at that time, had been given a gift of a big, beautiful crown by this rival king. And he said, something is fishy here. I don't like this guy. He doesn't like me. Why is he giving me this crown? It was beautiful. Looked like it was solid gold. Big, heavy. And he said, Archimedes says, hey, I don't know if this is pure gold. I think he may be cheating me, making it seem like a big gift, but it really isn't really all that big. Maybe just gold plated. Can you figure out if it's gold or not? And Archimedes pulled out his knife and said, sure I can. He said, no. Don't damage it. If it's real, I don't want it damaged. I just want to know if it's gold all the way through, but you can't scratch it. You can't cut into it. Archimedes said, whoa. He went about his business, and here's the rumor part. They had what they called public baths, okay? Roman baths. This was way before Rome. But anyway, he was in the public bath, and they're bathing and thinking. And as he sunk down into the water, he noticed the water level rose. Now, he was displacing so much water. And he said, just that little act, he said, Eureka, which means I have it. And supposedly he jumped out of the bath and went running to tell the king. But being a good scientist, good mathematician, he forgot to put on his clothes. Now that's the legend, that he went running to tell the king, running down the street saying, Eureka, I have it, because he had figured out how to do it. If he took the crown and lowered it into a pan, a big pan that was completely filled with water, completely filled, and lowered it into it, the water would spill out. He would catch the water, the volume of water that came out, and he would know the volume of that crown. With all the little intricacies and stuff, he could get exactly the volume because the crown displaced that much water. He could put it on scales, whatever they used for scales back then, and determine its mass. And by looking at the mass per unit volume, the mass itself didn't tell him whether it was gold. The volume itself didn't tell him whether it was gold. But the ratio of the mass per unit volume, that gave him the density. And the density for gold is different from the density of every other metal out there. It's an intrinsic property of gold. And he could take some real gold, determine its density, and compare the density. And if it was real gold, it would have the same density. If it was fake, plated, or something else, it could not have the same density. Okay? I guess that was worth running naked in the streets for. But he pleased his king anyway. I don't know whether it was real or not. That part of the story was never recorded for that. So it's characteristic of a given material. If you know the density of a material, the mass per unit volume, you know exactly what material it is, most of the time. Now, we in the U.S. customary, since we don't use mass, we use weight density, which is weight per unit volume, which will be in pounds per cubic inch, pound per cubic foot, or something like that. So here is the symbol. This is the equation for this. Density. Now, why they don't use a D, they use D for distance or something. So the symbol they use for density is rho. That's not a P. That's a Greek letter rho, which really is closer to our R than it is D. So why they use it, I don't know, but it's mass per unit volume. Now, this is an equation. These symbols this is not meter. This is a symbol, a representation of mass. This is a symbol for volume. This is a symbol for density, rho. These are just symbols. These are not units. So don't get units and symbols confused. Sometimes they'll treat them similar, but they're not. Okay? Now, just a little thing. Why did they use a capital V here with a little m? Anyone have a clue why they would do that? It seems inconsistent, doesn't it? I should take off points for that, right? Just kidding. No. Here's why. In physics, when we see a little v, we think velocity. Capital V, volume. They have the same letters, so the symbols, this is just the convention. Okay? Later we'll talk about little t is always time. Capital T is always temperature. So we use our symbols and try to keep them separate so they stand for certain things. And since we use little v for velocity, we use capital V for light. I don't know if we use anything for capital M, so we won't go there. But rho, that's a little rho. So there's the symbol. this is the formula or the equation that we use to represent the density ratio. Density is mass per unit volume. And frankly, folks, if you keep the units with it, if this mass is in grams, this volume in cubic centimeters, grams per cubic centimeter, that would be your density. If the mass, however, is in kilograms and the volume in cubic meters, that would be kilograms per cubic meter. Just like we said before, don't just give me a number, give me a number with a unit. Even these compound units, they tell you what you're dealing with. Okay. Here are four identical cubes. Every one of these cubes, now these don't look like good cubes to me, but we'll take your word for it, is 1 centimeter on a side. So this is 1 cubic centimeter. Every edge of every one of these is 1 centimeter. So these are equal volumes of 1 cubic centimeter. But if this were gold, if that were pure gold, like Archimedes was seeing if that crown was, that would have been 19.3 grams per cubic centimeter. Of course, Archimedes found they didn't use cubic centimeters. Whatever they were using then, he knew what it was. That's what the density of gold is and always is. Iron, on the other hand, pretty heavy metal, but nowhere close to as heavy. In fact, half the density of gold. So if that was iron underneath with just gold plating, he could have told. Big time. 7.9 grams per cubic centimeter. If that had been water, remember the density of water? 1, because that's how we define what a gram was. It's the mass of 1 cubic centimeter of water. So that has to be exactly 1. So this is a standard. Water is a standard for density. Because in metric units, it's 1 gram per cubic centimeter. Air, on the other hand, I think you mentioned air before. 1 cubic centimeter of air is only 0.0013. That's 10 thousandths of a gram per cubic centimeter. Air does have mass, okay? It's just not very much. Does air really have mass? Do you know if it does? Can you prove it does? How? Okay. Here's one way. Take a football, basketball, volleyball, any kind of ball, brand new, deflated. Put it on the scale. See how much it weighs. Then pump it up, put it on the scale. Guarantee you it'll weigh more. Well, now you're weighing not just the football, you still got the football or whatever ball it is, now you've also got the mass of air inside of it. You'll see it does have mass. Not a lot, but it does have mass. Okay? Another way. You pump up your tires. Okay? What do you use to measure what you're putting into your tires? PSI. What does that stand for? Pounds per square inch. What does pounds measure? Weight. So yeah, the air has weight. How many pounds per square inch? By the way, there's a ratio. That ratio is pressure ratio. Pounds per square inch. Force per unit area. That's what you have with pressure. That's what pressure is, force per unit area. Just like density is mass per unit volume or force weight per unit volume. Okay. Now, symbols and equation. We just had an equation. What was that equation? You remember it? Yeah, density is mass per unit volume. Rho is equal to m over v. There is an equation. So the symbols represent the quantities. What represented density? Rho. What represented mass? Little m. What represented volume? Capital M. Okay? These represent the quantities, the measured properties. Now, when we're measuring those things, the rho would be measured, the density would be measured in grams per cubic centimeter or kilograms per cubic meter. Okay? If it was mass, weight density, pounds per cubic foot or something like that. Okay? They represent the measured properties. But the symbols are what we use to represent them in the equations, and the units are what gives you what the reference are. The equation, they set the relationship. Mathematical relationships between the properties. I've already given you another one. Pressure is equal to mass per unit, the weight per unit volume. Okay? No, weight per unit area. I'm getting off that stuff. Okay. These describe properties, concepts, specify relationships. That's what equations do for you. Can you think of any other equations? Literal letter type equations that tell you exactly what you're dealing with. Let's go back to that basketball. Okay? And you blow it up. What can you tell? What is that shape called? A sphere. How can you describe the properties or relationship of that sphere? What formula tells you that? The volume of the sphere, you want to know what that is? A weird fraction. 4/3 pi r cubed. Pi is a number. It's an irrational number, it's a number. R, circle. What's the area of the circle?
Power square.
Yeah, I always thought pi were round, but no pi r squared. Never mind. Yeah, you're right. Okay, pi r squared. Area of a circle is pi r squared. Area of a rectangle is, you already given it to me. Length times width. There it is. Those are equations that represent relationships between properties. Area is length times width, pi r squared, volumes, length times width times height, 4/3 pi r cubed. All those are relationships, properties, concepts. Boy, what beautiful words those are. More math. Okay. All right. There's a couple of types of proportionalities we use. Okay? The first of these is called direct proportionality. Can anyone think of what we mean by direct proportionality? You got it. That's it exactly. Okay? The other would be an inverse proportionality, which would be increasing, the other one's going to decrease. This one decreases, that one's going to increase. You got it. How do we represent? And then when we have these proportionalities, we can make them equations rather than proportional to by adding a proportionality constant. For instance, area of a circle is equal to pi times the radius squared. Well, the radius squared is a quantity. Pi is the proportionality constant between area and square radius. It's the proportionality constant. That's, huh? Yeah, you got it exactly. Okay. Okay. And I bet you do all of you know Ohm's law? You don't, okay. Oh, you've had it already in your studies in cards. We'll get to it in just a minute. Now, sometimes these proportionality constants are numerical constants, like pi. Actually, pi is defined to be, if you had a circle, pi is the ratio of the circumference of that circle to the diameter of the circle. That's exactly how we define pi. The ratio, and that's a numerical constant because the circumference of the circle is a length, the diameter is a length, so when you take the ratio, divide them, the lengths go out, and you're left with a pure number. So that would be a proportionality constant that is a pure number, a numerical constant. Others of them have units, like a density ratio would be grams per cubic centimeter or something like that. Okay, here's your direct proportionality. By the way, this funny looking symbol there almost looks like the Greek letter alpha. I don't think it is quite. I think it's a little fatter than alpha. It also sort of looks like the fish symbol that you see sometimes. Okay? But this is a proportionality symbol. What this says is A is directly proportional to B. Just like you were saying, as B increases, A up. Okay, as B increases, A also increases. They really put this in strange places. As B decreases, A also decreases. That's a direct proportionality. And you represent that by the proportional symbol. Okay? Now, one that comes to my mind, this is sort of weird. Let's say I'm driving home tonight, which I plan to do pretty soon, okay? And let's just say I have 20 miles to go. That's just round numbers, probably a little bit less than that, okay? If I go at a constant speed, the longer I drive, the further I go, right? So wouldn't you say the distance is proportional to the time, right? Longer at a constant speed, that would be it. The constant speed is your proportionality constant, okay? That's a direct relationship, okay? Now, an inverse relationship would be A is inversely proportional to B, meaning it's proportional to the inverse of B, or you put 1 over B. Now, if you increase B, what happens to A? It decreases. If B goes from 2 to 3, that would be from 1, A would be going from 1/2 to 1/3. A would be going down, B would be going up. Or if you decrease B, say this was 4, and you go to 3, A would be going from 1/4 to 1/3. 1/4 is less than 1/3, but 4 was greater than 3. Okay? So this is an inverse relationship. A is inversely proportional to B. Okay? So I'm driving home again. Okay? You can tell I'm really getting anxious to go home, right? I'm driving home again. Okay? Would you? And let's say the distance from here to home is the same, right? If I drive at a larger speed, what will that do to my time?
Decrease.
Yeah, increase the speed, decrease the time. That's an inverse proportionality. My proportionality constant, the distance I'm driving. That's what stays the same. That makes sense, doesn't it? Okay. So, let's go back to the direct proportionality. A is proportional to B. How do you write that? Change it from a proportionality to an equation. You put, instead of the proportionality sign, you put equal K. Proportionality, proportional to, changes to equal K. And that makes it an equation. A is equal to K times B. So if I'm driving home, I drive longer time, I'll go a further distance. The proportionality constant has to do with the speed I'm driving. Actually, it works better. Yeah, this is distance, that's speed. This is speed, and this is time. Miles per hour times hours, that gives me miles. So you see units are your friends. They have to keep things. You change for proportionality, it's proportional to B, put equal K, and you have A is equal. That's your proportionality constant. And sometimes that'll be dimension, like miles per hour. Sometimes it'll be just a numerical constant, like pi, if you're talking about things at the same units. Same things work with inverse proportionality. And since they didn't put it, I'll put this one down. This changes to A is equal to K over B. Okay? And this would then be, it goes from A is inversely proportional to B, or proportional to the inverse of B, which would say inversely proportional. It changes to A is equal to K over B. You change the proportionality sign, equal K over B. Okay? So that's how you change proportionality to an equation, to an equality. Equal B rather than, equal K rather than proportional to. Make sense? That seems like a good place to stop. Okay? Next time we'll pick up with the nature of science. Okay? Now, folks, I'll say this every chapter. Oh, yuck. We've skipped some examples. We'll go back and do examples 1.1 and 1.2, but we'll pick up with the nature of science. Now, sorry I skipped these. I wasn't turning in my book.
Now, the class is normally going to be straight through.
No, okay. Most of the time, like next time, we'll have class for an hour, 2.5 hours, then we'll have the lab.
Well, I'm talking about it's going to be no break.
Oh, wait. Usually there'll be a break between class and lab.
Okay.
Now, if you need breaks sooner, I can stop and give you a break.
Well, it's not that, but it's just like,
What's that?
we've been in here for like, rolling up on 5 hours. I can't sit there and be still that long.
I know. Well, y'all had your trip over there, your practice and stuff like that. But yeah, if y'all need a break, just say, hey, we need a break. We can stop anytime. I just get carried away sometimes. What's that?
I'm gonna bring a recliner for the 64 hours.
No, you'll be falling asleep then. Okay.
Yep.
Okay. We'll see you Thursday. Most of you anyway.